Good afternoon. It is time to start the second joint seminar of ECFA, NUPEC, APEC communities, Jenas. The first one of the series took place in Orsay from the 14th to the 19th of October 2019. I am very happy to see you with so many participants representing the scientific of the three communities, the funding agencies, as well as representatives of large international projects and collaborations. The objectives of this seminar is to bring together the particle, nuclear, and astroparticle scientific communities to explore synergies and highlight recent achievements and challenges. In the previous meetings, there were some identified an expression of interest that will be revised in this conference. So this is really a conference with homework. Without further ado, let me introduce you the General Secretary for Science and Innovation, Raquel Lloti, that together with Jesus Marco, Vice President of Science and Technology of the Spanish Scientific Council, will inaugurate this conference. So please, Raquel.
Thank you, Maria Jose. It's a real pleasure to welcome to all the particle, nuclear, and astroparticle physicists and scientific communities at this second Jenas Symposium hosted here in the headquarters of our Spanish Research Council and organized in collaboration with ECFA, NUPEC, and APPEC committees. After the first meeting held in Orsay in 2019, and after these 2 difficult years marked by the pandemic, I'm sure that the second physical meeting of Jenas with more than 170 participants and 70 speakers will be certainly a success. Jenas means multidisciplinary research, an approach that allows researchers to cross boundaries to produce new science. Jenas joins researchers of the most important national, European, and international research organizations in the fields of particle, nuclear, and astroparticle physics, offering researchers the opportunity to share each other's activities, identify challenges and potential overlaps, and promoting possible collaborations between them to seek opportunities to advance in the understanding of the nature of matter. The Spanish Ministry of Science and Innovation strongly supports these communities. Since 2009, the Virtual Center for Particle, Astroparticle, and Nuclear Physics has certainly reinforced the connection among scientists and institutions on these domains and in our country, and has helped to consolidate their international impact. We are also convinced of the importance of offering our researchers access to the main research infrastructures, unique tools to produce outbreak science. In this sense, we are doing important investment for upgrading the experiments at Cern, supporting research institutions for their participation in international neutrino physics programs like Hyperfine and Dune, or hosting and building the northern side observatory of CTA in La Palma, Canary Island, among many others. Moreover, Spain has offered political support to the future Einstein telescope, the third generation of ground-based gravitational wave detectors, a proposal recently included in the ESFRI 2021 roadmap. We are promoting all these actions well aligned with the European Strategy for Particle Physics, the NUPEC long-term plan for nuclear physics, as well as the corresponding APPEC plan for astroparticles. And overall, with the support of our national research facilities, such as the centers of our Research Council, thank you, Jesus, also CIEMAT and main universities along the Spanish territory and infrastructures such as the underground laboratory of Canfrant or the National Center for Accelerators. During the symposium, you also foresee to discuss about data and computing, and this is also one of our priorities. Spain has a Cern's Tier 1 in the peak, and we are doing strong investment in our National Supercomputing Center in Barcelona for becoming one of the Euro HPC pre-exascale computers which offer service to a broad community in different scientific domains. In addition of the scientific returns, the participation in large infrastructures and big collaborations bring technological and industrial returns, which are essential for mobilizing the industry of science and contribute in a straight way to socioeconomic impact. To this aim, Spain is promoting the establishment of medium and large-scale infrastructures that will help to this goal. An example that I would like to mention is the PRISMAC project, a collaboration with Cern aiming to develop high-field magnets for future accelerators where CMAT and our state funding agency for innovation called CDTI are working together, and is our intention to extend these actions to other scientific domains. Our ministry is aware of that the experiments and the instrumentation in particle, astroparticle, and nuclear physics are of long duration and require a long-term compromise as well as established procedure for supervision and follow-up. The new Spanish Science and Innovation Bill, now in Parliament, includes for the first time in our country a pluriannual plan to provide adequate funding for research and innovation. And this bill is also focused on the needs of the scientific community, and especially on offering a more stable and attractive research career especially for the young researchers. We're aware of the importance of developing a stable mechanism to enhance the long-term participation and presence of young Spanish scientists in large-scale facilities, providing sufficient funding to support them, and capitalizing in their experience, facilitating their return. And I wouldn't like to conclude without pointing out the importance of training and formation in our researchers and engineers. Building detectors and accelerators of the highest performances are only possible if we have a solid base of human resources who have the competences to respond to the needs and challenges we are facing. Spain is committed in the promoting of these actions in the frame of our participation in large infrastructures and collaborations, working together with the rest of our European partners. I wish you all a fruitful meeting and express my gratitude to the local committee. Thank you, Maria Jose. Thank you very much for your effort. Thank you, the three committees that are organizing this symposium today. And of course, thank you to the CSIC for hosting it. I hope you a fruitful meeting today. Thank you very much.
Okay, good afternoon. I'm Jesus Marco, Vice President of Research at CSIC, the National Research Council in Spain. So first of all, welcome to all of you. We are very happy to have you here. Many thanks, Raquel, for this very nice overview of all the effort that our ministry and, in fact, the Spanish society is doing in this field. Many thanks, Maria Jose, for the organization of this. Yeah, I can take out my mask. Of this nice conference, and also to the committees. And as you may know, I'm familiar with this field. So I have prepared a short presentation. I think it's now in the screen. And no, I will start with a short quiz maybe you can start the video. So in these not easy times, CSIC as an institution addressing many areas of research, I don't know if they will start the video, and maybe some of you have seen that we are not really the man in haste. If you have seen our facade that is just here, it's very popular in Netflix in the past months. And I just included a video that maybe will be shown describing how CSIC is involved in many, many other fields, but at the end, you can find in many, many cases, and that is maybe not surprising for most of you, we can have a link of these problems with other areas like our area. And I leave this to you to discuss at the end of or to say a few words at the end of this short presentation. Okay, that's enough. It's the Volcano in La Palma last year, the end of last year. So what is the relationship of this with our area, no? So coming back to the presentation, please. I'm sorry to do these complex changes. Okay, CSIC in one slide. Maria Jose gave me the opportunity to make some promotion. We are around 13,000 people working in many areas. We have around 14,000 papers also by year. Our budget has increased to more than 1,000 million euros, and we have centers around across whole Spain, more than 120 centers, in almost half of them in collaboration with universities, and we have also strong collaboration with many other research centers, starting with CIEMAT, also with others that you know quite well, like IFI, and of course we have collaboration in the three areas, in nuclear physics, in astroparticle, and in particle physics. Now it's my turn to move things. Okay. We are also quite active on the support infrastructures at the national scale. You can see there our Caralto Observatory for astronomy, the clean room, large clean room that has produced some of the pieces of instrumentation and sensors that are employed across the many research centers in Barcelona. Then we have also the float, we have an Antarctic base, we have also the Botanic Royal Garden, the National Museum, and a few others. And we are also quite active at international level with more than 700 projects at H2020, that closed last year, and also other international projects in other areas. We are also active on knowledge transfer, being the first institution in Spain with patents, and also with some of them, as we are very proud, like the licensing of our serological test to the WHO that happened just a few months ago. Regarding outreach, that's one of the topics that will be also touched in this conference. We are also very active. You may see that we have more than 15,000 actions per year. And for the media, we have, in particular, after the pandemic, we were very visible, and we have more than, as you may see here, 13,000 press notes per year. Okay, but here I brought just, Maria Jose told me, why don't you say a few words about well, in fact, what you do very well. It's just writing about the strategy challenges. That is what you're exactly going to do today for your area. So almost 3 years ago, we made this effort at CSIC of preparing some white books, in particular 14 white books on the topics that were initially intended for 2050. At the end, we realized that they were reaching up to 2030. And it was really an effort made by more than 1,000 researchers. We published these 14 books that are available. And I wanted to comment on the volume 9 that was coordinated by Maria Jose Costa and Rainer Schodel from the high energy physics and the astrophysics communities. And with all these topics that you may see are very familiar to you. And the good point was that this triggered a lot of collaboration and exchange of ideas between all these participant centers. And well, the topics you see, but I wanted to bring these few lines about the challenges that do know very well. But sometimes when we are really in the middle of our research, we don't realize how obvious it may seem to someone from outside that we have not solved the problems yet. In particular, I just wrote there, yes, we do not understand yet why there are 3 generations of leptons, no? And this is one really challenging point. We have read the recent discovery of gravitational waves. That's another really clear change in the last years. And on the other side of the slide, you can say an important point that you're also very aware of is the relationship of advancing in science with the technological developments. This is also one important point for CSIC that we wrote in the book, but not only for technical advances. Also, we have mathematicians, and that's written there, new mathematical developments in the fields of geometry and analysis are also essential for the challenges. Maybe we don't know, we need a revolution on these basic methods that has not happened really. Yeah? Okay, in fact, we have also promoted in the last years the collaboration between different fields. And I wanted to bring you here one of the examples that we have. We launched aligning with the missions initiative from EU. We launched more than 13 initiatives, and one of them that I wanted to comment in the next slides is the one related to quantum technologies. And you can see here an example of what we do. We joined 33 research groups, 19 centers, 4 research centers and universities, 6 companies, and working on quantum communication, hardware for quantum computing algorithms, quantum sensors, organization, ecosystem, and training of all this area. With the results that have been reinforced by the recovery, transformation, and resilience plans supported by the ministry. And we are collaborating directly with companies, and we are really addressing specific projects like this link of the QKD lab, our QKD lab just across the street, to the quantum ring. Okay, so these are examples of collaboration, and I bring here the example of quantum, the developments on quantum, because this is one of the fields that we see has a lot of opportunities for collaboration with these areas, with in particular with astrophysics, astroparticle, and particle physics, as you well know also. This is, I think, my last slide. We are also very active regarding digital science and innovation, in particular open science. We have a very active digital repository. We have also progressed with the agreements with editorials to move towards publication under open licenses. And we are also founding members of the European Open Science Cloud, where we see this as an area where we can develop our, let's say, the platform for computing in the future. Okay. Well, I hope this last slide that I just included at the very last minute is an important point, and in particular, astrophysics and high energy physics has been included as a topic for the complementary plans with autonomous regions. And this means a lot because it means that we will also have coordination with these plans that in many cases, in particular with the centers that are supported at regional level, have a substantial funding. And this is important. This is the first time I think that this global coordination effort is done in Spain. Okay, so that's all. Thank you very much. I want you to tell me what's the relationship with volcans and high energy physics. Maybe some of you have an idea. A direct connection. Muon tomography. No?
We saw the eruptions and the TPC chambers, the shockwaves that happened.
Okay, so that's just a point. That's how rich science is and how many open areas we have in front of our eyes. Thank you very much.
Although it's not totally usual, we have some minutes. So if somebody wants to ask a question before they leave the room.
We don't leave them.
Okay. Thank you very much for staying. And that gives an opportunity really have any questions. So if you have any hot question, you can put it. If not, we will start with any question? No? So then, thank you very much, Raquel and Jesus. I think we should. And then we are going to start. We are going to call Sibran de Jong to do the presentation about challenges and highlights in astroparticle physics. So you will have here this one.
Okay.
And I will put the talk for you.
So thank you very much for the introduction. Could I please ask, is it possible to switch off the lights on either side of the screen? Just to improve the contrast a little bit. So while this is happening, well, thank you very much for inviting us, I should say. I'm actually sort of a stand-in for Silvia Pascoli, who was supposed to give this talk. But when it was decided to meet in person, it turned out that she couldn't make it. Now let's see if this works. So I'm also the APEC Scientific Advisory Committee Chair. And as such, I base most of what I tell here on a report that we've written in the context of the update of the APEC strategy, the midterm review report. And there's a number of people that I have to thank for their contributions to this talk at the bottom. So what will I do? Now this will be one of the few transparencies with text, because what I will try to do is to make the complement of the midterm review report. As you will have seen or not, in this midterm report, actually there's lots of characters, there's lots of lines and sentences, and there's only one picture. And that one picture will be the overlap with my talk. So what will I try to cover? Well, first of all, ask myself, what is the field of astroparticle physics? And especially since we're in a mixed audience, it would be good to talk about that. And I'm sure that Andreas later on for the policy part will also pick up on that. And then we go to the content, and we will look at particles and waves and fields from the universe. We'll talk about particles that we know from the standard model. We'll talk about particles that we still don't know from another theory. And we'll also talk about space-time properties. And then there's also a part of non-accelerator experiments. So not necessarily looking up at the sky, but doing experiments on ground. And there's two experiments I want to mention, and I was already pointed that the second one is maybe not an experiment, but for neutrino properties, there are lots of experiments on the ground. And then there's this thing called EUCAPT, which I also consider an experiment that is actually bringing astroparticle physics theorists and phenomenologists together. And that's also one of the first international collaborations on this with a home base at Cern. And then I will cover something about ecological footprint and come to conclusions. So, what is astroparticle physics? Well, we're looking at astronomical objects, particle accelerators in the sky, which emit particles, and then we try to catch them on the ground here or with satellites, and we try to deduce what is happening in the universe. And on the way, we can also do things about the properties of these particles. And depending on the type of particle, some of them reach us more or less directly from the line of sight of the object, but some others don't. They actually swerve around in the universe before they reach us. Probably all familiar with that. So looking at the particles that we know of as they're coming from the sky, we can distinguish a number of stable particles. So one set of stable particles are nuclei, atomic nuclei, and the energy spectrum is shown here with an energy in GeV, so it's at the end of this scale, and they come down all the way from like MeV region, and there's a very steep going down of the rate with energy, and they reach all the way up to like 100 exa electron volts, so enormous energies. much more than you can make with man-made accelerators. The second type of particles that we see in this graph are neutrinos, and we measure neutrinos in this range, typically, of PeV to TeV to PeV. And we see that the number of particles, which is depicted here, actually multiplied by E squared, because that's the normal slope with which they fall off as a particle. You see that it's nearly flat here. And the level is about the same as that of the nuclei, but then about a factor of 1,000 down in energy. And then we have the photons here, which is another type of stable particle, at much lower energies. So at the TeV scale, and they're often called gamma rays. Now these particles signify different distances in the universe. Because especially photons, the universe is opaque to, the universe is transparent to photons up to this type of energy, up to the TeV range or a bit higher. And then it becomes intransparent. Because of pair creation, photons travel not very far through the universe. And then there's a region where we have these nuclei, protons, and heavier nuclei which reach us. And they reach us up to energies of like 10 to the 19 electron volts. And then the universe becomes opaque again. And then we have neutrinos, which actually come from all the way through the universe, and they're unhindered in their propagation. And the new kid on the block is that we have gravitational waves, and they're also practically unhindered when they travel through the universe. So given the energy of the particles and the type of particle, you can look into the universe at different distances. So ultra-high energy photons, you can only see from things which are relatively near. Ultra-high energy, above ultra-high energy protons, you can also only see from relatively small distances. So this whole set of particles then gives you a lot of information if you can measure them all together and interpret them all together. So then we come to the other theme of this talk, is to make sense of all of this, you will have to connect it by theory and phenomenology. Okay, now we dive into the individual results. And I start with gamma rays. So these gamma rays, these very high energy photons, they mostly emanate from either pion decay or from upscattering low energy photons by high energy particles. And that makes that their energy is necessarily lower than that of the highest energy particles that are around where these photons are accelerated. So you see here the mechanisms for the highest energy. They're Bremsstrahlung. You can Bremsstrahl a photon of inverse Compton scattering, so upscatter a small energy photon, etc. And the news of the last couple of years is that particles have been seen up to TeV and beyond TeV energy, up to 100 TeV energy. And from that, and the fact that the particles that must accelerate these photons must have an energy which is at least 10 times as big, you can see that there must be particles of a PeV around in these objects that we observe. And there are various objects that are observed, like this is Centaurus A, this is a relatively nearby galaxy, and we see a photon spectrum. But it's also seen in the galactic plane by LASSO. So also within our galaxy there are accelerators up to PeV energy. There's more evidence for PeV energy accelerators, including those from Hawk. So we now have several pieces of evidence for PeV acceleration. Oops. And so that, given that, there's a need to look to the future. And in the future, we will build several new observatories. And the one that is most important for Europe is probably CTA, which will be built in two sites. One in South America and one sort of on the volcano that was just shown. Therefore also volcanoes are very important, especially for them not to erupt. And that will give us a huge increase in the number of sources that can be seen and in the precision with which these sources can be measured. And several prototypes have already been made and tested, and actually we see that they do the job as it should be done. Now another approach is the Southern Wide-Field Gamma Ray Observatory, which is another technique which is measuring the same gamma rays with water tanks. And that's a complementary method which was pioneered by Hawke. Then going to the next type of particle, neutrinos. We see here a famous event, which is an event from the IceCube collaboration. And this is the event that comes in coincidence with many other measurements of this blazar, Texas 0506 plus 056. And this is the first time that we have a positive identification of a source of a neutrino. So this was like the holy grail for many of these observatories. It actually has taken a long time, but now we have one. So this is an important step forward. And what it means is that these events are so rare, so you need bigger and more observatories. So from Europe, we're building a couple. Well, we're actually ending one, okay, which is Antares, which actually paved the way for deep sea neutrino detectors, and based on which now KM3net is building two types of detectors. One is ORCA, which is for particle physics, for neutrino properties, and the other is ARCA, to really do the astronomy measurements with neutrinos. Also already more or less done is Baikal GVD, also based on the same method of water. Now you see ice here, and of course the nice feature of the Baikal Lake is that it freezes over winter, so you can install your stuff while standing on the ice, and then when summer comes this all melts, and you have a deep water telescope. In addition to KM3net, there will also be an upgrade of the IceCube experiment, IceCube Gen 2, with various features, and notably, these detectors are getting multi-purpose detectors. So they're not just made to detect astronomical neutrinos, but also to do all sorts of other experiments with neutrinos, with atmospheric neutrinos. We hope for a supernova burst at some point in time. Not too soon, but not too late either, because we have to have these detectors ready and then see the burst. And the new kid on the block is RNOG, which is a detector which is using a completely different detection technique, using radio detection in ice. And it uses the Ascarian effect, where particle collisions in the ice actually radiate radio frequency signals that can be caught by antennas that are in the ice, and from which you can then reconstruct the event and the neutrino energy and direction. All this is now tied together with the global neutrino network, which is another important development, that we have all these alarm networks and networks that tie together the information of the different observations, also in real time, so they can be followed up in real time by other observatories. Now, the last type of standard model particles that can be seen from the universe are the nuclei. They go up to the highest energies that we've ever seen, but they have some disadvantages, namely that they're charged, and especially if they're not protons but heavier nuclei, they have several charges, and therefore they are bent in the magnetic fields that are around all in the universe, and specifically also in our own galaxy, which makes that you lose the connection between the arrival direction and the direction of the source. So this is complicating life quite a bit. There's been a very precise measurement now of the spectrum. There's a measurement of composition, what type of particles are they, which is at the very high energies a bit undecided. It's not necessarily, meaning that this is in the middle is not yet making it undecided, but probably makes it either one element or a mix of elements. Actually, the latter is more probable. And but then trying to see what the events are, event by event, that will be very important to be able to trace them back to to their source. And that is something that still needs to be established. What was seen is that for the highest energy cosmic rays, we see a significant dipole, and the dipole is pointing out of the galactic plane. So that confirms that the highest energy cosmic rays are from outside our galaxy and not from sources inside our galaxy. And then there is a particle physics problem that we see. In fact, in showers that we observe compared to the Monte Carlo, we see too many muons. And there's been lots of studies to see how you can bridge that gap, and it's not so obvious. For the future, there will be an upgrade of the Auger experiment, really aimed at trying to determine the particle by particle, or event by event, particle type of the cosmic rays coming in. And it consists of extra surface detectors on the water tanks that are already existing, and the radio detector, and also of underground stations with which we can then see, identify the muons in the showers, so that also gives us a lot of information. At the same time, the telescope array in the north hemisphere is extended to get a size which is approximately that of Auger, so effectively we will have an Auger North. Of course, a lot depends on how well these two collaborations work together to get a complete sky view. Then in the further future, we have a satellite experiment planned, Poema, and there are several plans for huge observatories. And these are observatories you have to think of between 20,000 and 200,000 square kilometers. So think of size of Spain. Okay, trying to move forward. It's hanging. I must have a huge picture there. Somebody assisting? Oh, sorry, yeah. Okay, sorry. I tried to switch back, but now, okay. It's just it's a big picture. Now, the one in the corner, okay, Grant. This is again one of these experiments which will aim at detecting cosmic particles, but at the same time also detecting neutrinos and photons. So this will be a multi-purpose experiment, also being able to detect many other make many astronomical observations and particle physics observations. So now I'm still hoping that the next slide comes up. Okay, no. Okay, we move on. So these were the standard model particles, and we're also looking for particles that do not exist yet, which is what we call dark matter. Now, in over the past decade or so, people have come to realize that we were always expecting dark matter to show up, sort of just around the corner, a little bit higher in energy than we were used to making particles at colliders, but we now realize that they may be sitting there at an enormous range of different masses. And there's a sort of a split in that for the very low masses, these particles are connected to the QCD-CB violation problem, and they're called axions. So this is like one set of theoretical inspired models, and the other ones is to fix the electroweak model with something called WIMPs, weakly interacting massive particles. To detect these particles, there are several strategies, or actually, one is actually to make them, which I will not talk about, probably Paris will talk about that. And then there is something called direct detection. It's just, you hope that they rain from the universe, and then you make a detector to detect them, which means that the dark matter particle scatters off a standard model particle, and you collect the signal of the recoil. And so there are several technical ways of doing this detection of the recoil, which are depicted here, and I'm not going to go in detail, because I have to watch the time a little bit. But the situation at the moment is as follows. There are a good number of experiments that are detecting or trying to detect through direct dark matter detection these cosmic particles. And this is the energy range covered for this weakly interacting massive particle, running from the hundreds of MeV region to the TeV region. You see that where they measure the cross-section limit, that there's a steep fall here for the low energy, so there's a little bit of a hole. And then there's like a nearly flat region here in the GeV to TeV region. And there's a large number of experiments. And the leading experiment, which actually is the one with all of these blue references, is Xenon. And this is the results from Xenon 1 ton. The other important experiment here is Panda 4 ton, which published a limit which is actually a little bit better in this region from 10 GeV to many TeV, to 10 TeV, than that of Xenon 1 ton. So there are competing experiments. But we want to go down because these are limits. So this actually means that we haven't seen these particles. I'm trying to advance again, but uh-oh. Okay. Oh, sorry, then I have to still go back to point out two regions. So there are two spots here in the middle called Dharma. And there was a supposed detection by the Dharma experiment. And the detection was that there was an asymmetry when looking at the different directions with respect to our galaxy. So we move through our galaxy. If the dark matter would be more or less static in our galaxy, then of course from one direction you would see more than from the other direction, because like headwind and tailwind. And the Dharma experiment actually made a measurement there, which was significant. So a lot of, found it. Now I'm going back to the next slide with some effort. I should have switched order. Because the first thing I want to discuss is Dharma. Oh boy, this is slow. Yeah. No. Okay. So other experiments now also look for this annual modulation. And for example, the Cosine 100 collaboration a few years ago published a non-signal, so an exclusion, which encapsulated the Dharma regions. So saying that, well, we don't agree, okay? We cannot confirm this. And more recently, last year, the NICE experiment have their first 3-year result, and they have the same finding, that they don't see the Dharma Libra excess. So apart from the fact that all the other experiments didn't see it in the direct dark matter detection search, also trying to do the annual modulation makes that this Dharma Libra result is probably the outlier, and all the others see nothing. Now the other excitement, of course, was that in the Xenon 1 ton experiment, which produced many of these results on the previous slide, an excess was seen at very low recoil energy in the KeV region. And so there have been many speculations on what it could be. And the outcome of that is that, well, you need a better measurement to make sure that either this is not there, or which of the explanations it may be, and whether it's really there. So it's a little bit undecided, but still sort of very exciting that something is seen. Which means that you need, again, better and also larger detectors. A step forward is the Xenon Anton detector, which is currently under test. The TPC turns out to work very well. So this is about a 6-ton liquid xenon target, and with an impressive concentration of background material, so very low background levels, which is largely due to the purification system, which works quite well. In the competition, there's still the Panda 4 ton liquid xenon, which is operating, and there is also the LZ experiment, which is about to start operation. Now, the interesting thing is that if you look at the pictures, they look pretty much the same. So it's all like a cylindrical vessel with liquid xenon in it. And also the detection mechanisms are not that different. So, but before going sort of on what that means, first a digression into the low energy dark matter. So these are the axion particles, and actually there's a whole slew of theories which have axion-like particles. So that's why they're now called ALPS, axion-like particles. And the axions are particles that interact with light. So they have the same U1 symmetry breaking, or the same U1 symmetry, and one actually is breaking it and the other isn't. But they have a connection, the photons and the axions. So the purpose of all of these experiments is to switch between axions and photons. And the trick to do it is magnetic fields. So either you make a resonator with a magnetic field and try to resonate these axions into photons and detect them. More specifically, you can also make a strong magnet and then look at a possible source of axions, and a possible source of axions is thought to be the sun. So you look with a helioscope to the sun and try to see if you block the sunlight, you still have light to see, which would then be from the axions converting in the magnet. And another experiment would be to try and shine light through a wall. So that requires two conversions. So first you have a photon, then you want the photon to convert in a magnetic field into an axion, then the axion can travel through a wall, and then after the wall you use another magnetic field to convert the photon into, to convert the axion into a photon again. That would be light shining through a wall that you can normally not shine through. So these are the type of experiments. And well, currently we have these red line limits, and they're from a whole slew of experiments. CAST is from looking at the sun, but there are also all these experiments here trying to use resonators, etc. And the interesting band here, the band predicted by theory, would be this colored diagonal band. So you want to reach that and bite into that band to see if there are axions. Oh, I should have switched order a little bit in these slides. Oops, no. Sorry about that. So there's a set of new experiments being devised for basically for the helioscopes and for the light shining through the wall, and they are supposed to bite into this region. So with the EAXO and with ADMAX and MADMAX, they are supposed to bite into this region of possible axions, theoretically possible axions, with quite a coverage, but not a full coverage though. So probably even after, if you find nothing, then after that a next generation would be warranted. Talking about new developments, so future developments in the WIMP detection, there we see that the LZ, Lux Zeppelin collaboration and Darwin collaborations found each other, and they're now proposing a joint detector, a joint liquid xenon detector. Again, it's a huge detector, many tons of liquid xenon, so about 40 ton in the fiducial, with two methods of detection. And again, this experiment would not just be for dark matter searches, but turns out to be very practical. It's a multi-purpose experiment. Again, of course, it would detect neutrinos from supernova explosions, but it can also look at neutrinos from the sun. It can look at properties of neutrinos, and can also do things about cosmic rays and neutrinos produced in atmospheric showers of cosmic rays. So there's a large collection of things that can be done. For the dark matter, the aim of this experiment is to go down in sensitivity to something called the neutrino floor. And the neutrino floor is given here with this, what is it for color? Like brown-yellow color. And at that point, you see neutrinos, as if it were dark matter. Yeah. So now, you can think of that two ways, okay? Or one is that At that point, you will become background dominated by neutrinos. And of course, that would be, in that sense, it's bad. I always consider it like, okay, at that point, you can actually check your detector in the absence of dark matter, because if you detect nothing, you have a problem, because you should detect the neutrinos there. So you have a calibration signal. So it can also be a step forward. Okay, other things detected, low energy photons, cosmic microwave background. Now, in the last couple of years, not so much has been going on, but I put up this slide because we have to remember that when we talk about dark matter and dark energy, a lot of the evidence actually comes from here. So this is a reminder. And we have to make a step forward. And one is to go with an experiment called Lightbird, which is a satellite experiment. Basically doing Planck, but then much better, of course. And also the ground experiments. There's a 4th generation CMB experiment, or there's a set of 4th generation CMB experiments planned at the South Pole, and they will be important to measure the B-mode polarization, which is in some sense the holy grail for the moment in this cosmic microwave background detection. Stepping from cosmic microwave background to dark energy, this is of course what we think is the biggest chunk of stuff in the universe, based on, for example, the CMB background measurements. And there a number of new satellites are coming up. Or in fact, there are 2 ground-based telescopes coming up, DAISY and the Rubin LSST telescope. And then 2 satellite experiments, Euclid and the Nancy Grace Roman telescope. And they measure different things. So in the dark energy, there are basically 4 signals that you can detect. Supernova type 1a expansion, baryon acoustic oscillation, weak lensing, and galaxy cluster evolution, so how galaxies move. And we have a sort of an equal number of unknowns here in the equation for non-relativistic and relativistic matter, for curvature, which is a dark matter, which is a dark energy phenomena, and for the cosmological constant. And to disentangle these things, you need signals from different observations, and then you may be able to disentangle all this. So that's going to be important. Then for gravitational waves, well, we have made big strides forward there since the first observation. There have been 3 runs of observations, 01, 02, and 03. This is how far the telescopes look into the universe for neutron star mergers. And a large number of black hole mergers have been discovered, where each of these pairs then resulted in a heavier black hole, which is then drawn on top. So this is an impressive figure. And so you can actually start to do statistics on that, and notably also discover that intermediate mass black holes do exist and are actually detected. The other things you can do with gravitational waves is check Einstein's relativity, general relativity, and that has also been done already extensively. Now, unfortunately, the diagonal line here is what you expect for probability values for these tests when there is no extra component than GR. And the blue line is sort of meandering around it, which is the observation, and it pretty much looks like general relativity and not much more. Of course, the big news from the gravitational waves was the neutron star merger, which has also been observed by many other experiments, and from which we can deduce a lot more about nuclear synthesis. So there we have the overlap with the nuclear physics very prominently. So this was a big step. And of course, the step into the future is then to make better gravitational wave detectors, specifically ones that look further back into the universe, so at larger redshift distances and further into the history of the universe. There are 3 on the table: the Einstein telescope, the Cosmic Explorer in the US, and LISA, the satellite experiment with satellites millions of kilometers apart. For the Einstein telescope, there's good progress. There's a Pathfinder program to test at a small scale several new techniques. And specifically also there was news in the last couple of weeks from the Dutch government that they reserved 42 million for site preparation and for connecting to industry, and 870 million euros for when this Einstein telescope is to be built in the Netherlands. And also the Italians are working in the Italian consortium on a grant of 100 million for site preparation. And they're aiming at 900 million for when I guess the telescope will be built at Sardinia. So actually this looks really good. So I think the probability for having an Einstein telescope improved enormously over the last couple of weeks. Okay, neutrino properties. This is the only diagram that overlaps with this midterm evaluation. Of course, there's new mass measurement from Katrine, but that can be improved further. Now, the problem is that we still don't know if we are in inverted or normal hierarchy. And so to improve on that, we have to make new measurements from a large range of new observations and crank down on the PMNS matrix elements. To also see whether we are in normal or inverted hierarchy, and also to see if we are in Dirac or in Majorana mode. Yeah, I'll finish soon. We have several experiments lined up in underground facilities for measurements of neutrinos double beta decay. Let's see. It's still slow. Okay, then one of my last slides, the UCAPT progress. So this theory platform has been established as a physical entity at Cern. It is moving, so it produced a white paper. There are many virtual colloquia and there are annual symposia. The first have been held last year, and the second one will be held on the 21st to the 25th of May this year. Okay, whoops. I will one slide back because I really want to show this. So there is one experiment that actually works on establishing what its ecological footprint is and what can be done to mitigate an excessive ecological footprint, which is the GRANT experiment, and there's a nice report based, which will be in the slides because I cannot sort of go back. Well, it's here. And it's sort of interesting to break down what really the problem is in our ecological footprint, in our carbon footprint. Okay, my summary. We have many observations from astroparticle physics and therefore many results, and this is sort of a very superficial collection. Theory phenomenology is a key in linking all these results from the different experiments and observations. We are ready for, in many areas, for a next generation set of detectors, and many of them are multi-purpose and multi-probe, so they can be used for many things. Many of them also still require R&D, which will be discussed later this week. They all require substantial funding, but it is important to have a variety of these observatories because then we can do multi-messenger astronomy, and that is a much enhanced science case. So it's important not to really select only a few of them, but actually to have a whole suite of experiments that reinforce one another. And then, of course, the most overlap is with particle physics and astronomy, not represented here, but there's also significant overlap with nuclear physics. Okay, thank you.
Thank you, Sigrid. A few minutes for questions. Yes, please, Faisal.
Yeah, thanks for this very rich presentation. The last comment or point about overlap with astronomy and nuclear physics, I'm curious to see what's your opinion about SKA. I mean, I would have expected that SKA be on a major project with objective covering many, even dark matter. Why is not within your
Why didn't I mention it? Yeah. Maybe it's also a national bias from my side. In my country, it's really an astronomy project. It could have been there. Of course, I have to apologize because actually I missed out many experiments here, and I already ran over time. But yeah, SKA is interesting, and specifically also with the radio detection of cosmic rays, there is an interesting overlap. In fact, directly also with astroparticle physics.
Maybe for a non-expert, where the frontier between astroparticle and astronomy is?
I have no idea.
Questions? No? So then we thank Sivran again. Thank you very much. And now we hear Paris speakers from Cern and from University of Athens that will talk about physics highlights and challenges in particle physics. Thank you, Paris.
So good afternoon, everybody, and first of all, thanks to the organizers for the invitation to appear here. It's clearly both a privilege and an honor. So you realize in 30 minutes we're not going to do the entire looking at what's going on in the field. So this will be a very, very broad brush summary. So first of all, a very quick introduction on where we stand on the road to obtaining answers. And then there's basically three major parts. One is the fundamental, the scalar sector, and the search for new particles. The other one is dark matter, in which I will only refer to collider searches, since the direct searches were already covered. And then finally, the physics of flavor, where I include neutrinos, quarks, and charged lepton flavor. So, where we stand today is obviously with an extremely successful theory. This is all, the pointer does not seem to be working. It is working. So these are all cross-section measurements, and they're basically in full agreement with the standard model. It is really an unbelievable description. And at this point, things are very simple. What we have to do is basically concentrate on this last particle, which is a particle like no other, as we will see in a moment, and this is basically the highest priority. Obviously, the physics of the other massive guys here, the WZ bosons and the top quark, is also very pertinent right now, because it may be the road, it may be the portal to some important new physics. So, what's the road to obtaining answers? Well, first is the physics of fundamental scalars and direct searches. So there we have the LHC, the high luminosity LHC, and the future colliders. And there we mean a potential future circular collider, or one of the linear collider options, and so on. This is the goal here, is to understand one of the strangest elements of the standard model. The second one is dark matter searches, where we have a very large number of experiments searching for direct detection of dark matter. And this was covered already. And then what we have is matter-matter collisions that can also create dark matter. Physics of flavor, where we have a complementarity between beams, such as dune and hyper-K, and on the other hand, reactors and atmospheric neutrinos. In the quark sector, we have kaons and the B physics system, and then finally high precision measurement. So this is basically the menu. Now, to orient everybody, the LHC and the high luminosity LHC schedule. The run one of the LHC was basically this bit here. This is where the Higgs was discovered. The total of what we have accumulated so far is something like 150 inverse femtobarns from run 2. Now, what we expect to have happen in the next 3 years, basically in what we call here run 3, is to accumulate 250 on top of that 150. And then finally, when the high luminosity LHC starts, hopefully in 2029, we expect to accumulate 3,000. So that's an order of magnitude more. So that's just to have some numbers in the back of our minds. Now, first, we have to pay homage to the incredible discovery of 10 years ago, almost to the dot, 2 months ago. There was these incredible events, a Higgs that goes into 2 photons, a Higgs that goes into 2 Zs, and then 4 muons over here from the Atlas detector, and then the actual first peaks. And you can tell here that we had basically a pithy 2 handful worth of events in those early days. Okay, we knew it was a boson because it went to 2 photons or 2 Zs. Then what happened following that is that we measured the spin-in parity from an angular analysis of the 2 muon pairs in ZZ events. This is analogous to pi 0 going to EEEE. That's how Steinberger measured the spin parity of the pi 0. And from there we discovered that basically this guy is 0 plus. So this is a particle that has the quantum numbers of the vacuum. It is a particle like no other. It is the only guy who can be created alone. Anything else, including Z bosons, they have to be created in pairs. There is no such other element in the Standard Model. The mass has been measured with incredible precision of 2 per mil, and by now we have seen all of its production mechanisms, whether they come through loops, gluon here, whether it comes from boson-boson fusion, radiation off of a W and Z, or from TT bar. All these things have been observed. And just to give you a feeling for the increase of statistics, that pitiful something like 10 events is now on the order of 200 events these days. So the field has advanced. The pride, what is really the new elements is that we have seen it now interact with the whole 3rd generation of fermions, because it goes, this is the Higgs to tau. If you do the background subtraction, you have a clear signal here. It also goes into BB bar, and it also interacts with TTH. This is not a mass here. This is, well, a BDT, an MVA, a multivariate analysis variable, because it doesn't decay to TT bar. It's only emitted in the final state. Hot over the last year or so is the coupling to 2nd generation fermions, where we've had for the first time some evidence for the Higgs going to mu. You don't really see anything in this mass spectrum of the 2 muons, but there is actually a small excess. This is evidence at the level of something like 3 sigma. And incredibly enough, with the advent of very powerful deep learning techniques, it looks like we might even be able to get a whiff at Higgs going to CC bar at the ultimate high luminosity LHC. Here's a summary of the couplings, and this is another stunning picture of something that we've never seen before. This is a new kind of force. This is a couplings as a function of mass, and you see that this is the ultimate non-universal coupling. It doesn't come from a gauge principle. It's not like the W bosons, the Z bosons, the photons, and so on. This is a completely different beast, both in terms of quantum numbers and in terms of interactions, which is why it deserves further study. Now, if you put it all together, all the studies from the E plus E minus collisions of LEP to the Tevatron, the LHC, and so on, and you do this gigantic fit of the Standard Model observables, what you have, you can concentrate on the right-hand side, which is this table here, where in blue you see the indirect determination from theory, and then in red is the global electroweak fit. The point is the actual measurement. So what you see here is basically very, very good agreement. And overall, the probability, the chi-squared, the probability for all of this to be true is something like 23%. So it's a very, very consistent picture. Now, if you're following the news, you may have heard that recently we've had some new measurement of the mass of the W boson. Very quickly, the mass of the W boson is actually very sensitive to what's running in the loops. So you have a quadratic dependence here on the fermionic mass and the logarithmic dependence on the Higgs mass. So if you plot the W mass versus the top mass, what you have is these lines here. These are actually parabolas, but they're so close to it that they look like straight lines. And then you have a logarithmic dependence on the Higgs mass. This blue here is where the Standard Model sits. These are all the mass measurements that we had up until something like a couple of weeks ago. And lots of top mass measurements, a dizzying list of them, W mass, and this is the total set of measurements. This was the Standard Model prediction. So things look good until a new measurement arrived from the CDF experiment, and it's sitting out here. And to make a long story short, this is a 7 sigma departure. So I just drew it by hand here. What you have is the top mass also moved just a little bit to the left. So the W mass has been bumped up all the way up here. So this would be the new point to be compared with the blue. So there's a major inconsistency here. We call it's in tension with the Standard Model. This is a new language for, in the old days, we would say it's in disagreement. Things that we should mention is that this result is actually the most precise measurement of any of the MW measurements up to now. It's also 3 sigma higher than any of the previous measurements, and it's 3 sigma higher than the previous result from the same experiment. So this is, I'm sure, will cause many a W mass measurement from now on. Now, what's ahead of us? In the scalar sector, first of all, with the standard model, well, the first major stop will come from the high luminosity LHC. To make a long story short, if you take coupling modifiers for all the effective couplings of the Higgs, to photons, to Ws, to Zs, and so on, and this is the expected sensitivity or the uncertainty on that coupling, at the end of the high luminosity LHC, we will have the bosonic modes known to something better than 2%, the fermionic modes down to somewhere between 3 and 4% in the worst case. Higgs to new things, for example, it going into dark matter particles like over here, we can constrain the branching ratio of that to less than 4%. And finally, the ultimate prize of all this will be to actually measure the shape of the Higgs potential. And you do that by looking for a coupling, a trilinear coupling here and a quartic coupling over here. What does that give you? It gives you information on the actual full shape as opposed to just the minimum, because we are basically living somewhere down here right now or somewhere over here. And there's a difference on whether the transition is something continuous and smooth like this, or it has a couple of minima. In other words, whether it's a first order transition. This is like boiling water. If you remember your statistical mechanics, the first derivative of the energy is discontinuous. So because it allows both water and bubbles to exist at the same time. And that would demand new physics. So what can we do here at the high luminosity LHC? The bottom line is that we can get a measurement of the self-coupling to something like 50%. Actually, perhaps probably better than that. This is a conservative figure. What about the long-term future? Well, you need a Higgs factory. It's as simple as that, if you want to go to the per mil level of accuracy. And the one thing about Higgs factories is that, for example, an EE machine, because that's what we're talking about here for the factory, is that the final state is basically a Z and an H. You only tag the Z. So the H is completely free to go to anything. So you have a completely unbiased measure of the Higgs width into these invisible modes. That's basically one huge advantage of the E plus E minus machine. And the lack of any assumptions on the final state. Bottom line is that you can get a width measurement which is accurate to 1 to 2% in the future Higgs factories. Then if you look at the couplings that we were looking before, the coupling modifiers, and there's a whole bunch of colors here. It's a very colorful transparency because it corresponds to different machine configurations. If we take the ultimate reach, which is the dream come true, that we get a future circular collider that gives us a Higgs factory, we do the top, and then after that we also go to 100 TeV with a Hadron Collider. Well, that yields measurements here for the bosonic modes, which are at a fraction of a percent, like 0.2%. We're at the 2 per mil level for these couplings. And the same thing holds true for the top coupling, that we can get to 1% and so on. This is the ultimate that one can hope to get. What about the Higgs self-coupling? There's two ways that you can get to it. One is through single H production, whereby you have TTH, but now you also have the Higgs loop, so therefore you get the HHH coupling here, or in an EE machine, out of, again, ZH, and the Higgs loop comes here with enough precision. And incredibly enough, for kappa lambda of something like 2, the hadron gives you 3%, the EE 1%. HH production, which is a real thing to go after, both at lepton colliders and at hadron colliders, is the one that gives you by far the highest sensitivity. And to make a long story short, you have the quartic coupling, the lambda, for the current Higgs potential, that you can get down to 5%, the ultimate measurement combination of FCC-EE and FCC-HH. The top mass that we saw earlier, that it's on this plane, is a very sensitive electroweak theory test. From a threshold scan, as you walk along the energy of an EE collider, you can actually walk it through and you can see the cross-section rise, and you can measure that with a precision of something like 25 MeV. It's more than an order of magnitude better than the 400 MeV that we currently have, only in terms of systematic uncertainty. As for precision observables, with a giga Z factory, the mass of the Z, the mass of the W, and sine squared theta W are going to be measured to incredible precision. So that circle that you saw earlier will essentially shrink onto a point. We're talking about a mass measurement of the Z of 0.1 MeV, 10 to the minus 4. So, what about going beyond the standard model? Well, there are four scenarios, but there's four main scenarios, which is compositeness, supersymmetry, contact interactions, new resonances. First of all, let's talk about another magic, which is the magic of the Higgs boson mass. Normally, the loops would give a mass that would be run away all the way to infinity. Well, no, not really infinity, because at some point you expect that gravity is going to kick in the loops. So you run the loops only up until lambda Planck. But then it also means that you basically, the most natural value for the Higgs mass should be the Planck mass. But it's not. It's off by about 17 orders of magnitude. Put differently, what stabilizes it? What keeps it so low? Now, this is the infamous naturalness argument. Now, people hate naturalness, though they also love it, because they say, well, this is a theoretical argument. Who believes in this type of thing? Let me remind you of how successful naturalness has been in the past, starting with Weishkopf, who was the first one who pointed out already for the self-energy of the electron that it's E squared over R, and clearly this thing goes to infinity linearly. In quantum mechanics, it goes quadratically with energy squared. And he's the one who showed that by introducing antiparticles, you tame that infinity and you only go logarithmically, and it's something that goes logarithmic with the mass of the electron. And the other grand example of many, actually, I won't go into rows and so on, is just the prediction of charm coming out of the lack of observation of k long going to mu plus mu minus, whereby from this loop over here, you would conclude that this runaway loop goes as g lambda squared. And if you assume that there's a C quark, well, it means that it's proportional to the C quark mass. And that gives you a prediction for where the new quark would have to lie. So this is the theoretical argument, but it served the field and physics extremely well over the past decades. Now, the scenarios, a composite Higgs, the word speaks for itself, something like Cooper pairs and superconductivity. So you would have a new strong interaction and so on and so on. Supersymmetry, you introduce a whole bunch of partners that basically cancel exactly in the limit of equal masses, slightly off if the masses are not equal. The fermions cancel the bosons cancel the fermions, since you introduce a full doublet. It's crazy, but antiparticles were equally crazy. Little Higgs, whereby the Higgs is really just a pseudo-Goldstone boson of another effective theory of, say, at 10 TeV. Extra dimensions, it speaks for itself. Now, all of these solutions introduce either deviations in the tails of distributions or new particles that you can go after. Higgs compositeness. You can try to parameterize roughly the reach of future colliders by using, going back to rows and pies, pi and interaction. So what you have there is a 3-vertex, a row or a Higgs with a coupling of G star, or if you remember the vector dominance model, things whereby a photon becomes a J psi, you have a GW over G star. So you can make a plot of G star versus M, and you can combine the 3 types of measurements. One is Higgs precision measurements. The other one is 2 fermion, 2 boson measurements. And the other one is 4 fermion and searches for W prime and Z prime. And what you have over here is the W observation, the 2 fermion, 2 boson. Here is the Higgs precision. And then on this side are the direct searches. You can actually take this and translate it into a limit on the compositeness of the various colliders. And the bottom line answer is that with this long-term future program, we would get to compositeness of the Higgs of 15 to 18 TeV, depending on the machine. The other thing, this is the halfway through the talk, refuses to change slides. So we take a pause for some commercial, it's a small commercial break, as they say. I don't know what to do. Is it battery, perhaps? Susie. We looked for it, haven't found it. And there's been a gigantic set of searches. That's the message of this slide, okay? But you can tell Susie refuses to go. I'm very sorry. Okay, long-term future. Given that we have probed the 1 TeV region, what happens, say, all the way up to 10 TeV? So there are basically 3 questions to ask here. If Susie is really there, okay, then what are the ultimate masses that we can reach on the superpartners? Is nature fundamentally fine-tuned? If the solution is Susie, then it's fine-tuned by how much? And finally, is dark matter a thermal WIMP? And does a Susie WIMP? Now, in terms of strongly interacting particles like quarks and gluinos, the answer is very simple. If you want to set limits that approach 5 TeV and 10 TeV, roughly basically twice the mass of what we will get with a high luminosity LHC, or 5 times that of the high luminosity LHC, you need a future hadron collider, period. It's the only way to probe the highest masses for the strongly interacting gluinos and quarks. This is not going to go very well. It's not flipping the slides. Electroweak Susie. I won't have time for this. Well, I'm losing time here. So, since it's still on, what you're looking at is charginos and neutralinos, which are the one thing that benefits tremendously from the current increase in the luminosity. And the reason is that this is one search which is actually limited by statistics. And what you see here is the mass of the second neutralino or the chargino, the NLSP, in other words, roughly the NLSPs, and here is the mass of the lightest supersymmetric particle. These are the exclusion regions. All the attention at the LHC right now is going into this difficult corner where you have very, very little energy, visible energy, as a result of which you can't really probe this region. Now, the high luminosity LHC here will actually increase the reach from this pithy region to all the way up to something like a TeV, always with little holes on this side. And then eventually, if there's a linear collider actually allows you to go all the way to the kinematic limit, for example, at click of 1.5 TeV, and straight up to the diagonal, because you can really make them all the way to the kinematic limit. In a hadron collider, what you have is limits like this that allow you to extend very high in mass. So this ultimate side on the right-hand side is limited by cross-section, and the limit here on the upper side is limited by acceptance, simply because you need to introduce cuts in order to see it. Bottom line, extremely important message is that a thermal WIMP out of Susie, you can actually exclude both in the Vino scenario and in the Higgsino. And why are Higgsinos important? Is because they are the partners of the Higgs, and if the Higgs is light because of the naturalness argument, Higgsinos have to be light because of the same rough argument. What about the dark sector and feebly interacting particles? So, the nightmare scenario, of course, for dark matter is that it be totally dark. That would be the only gravity interacts with it. That would be a disaster because you can't really do much experimental physics with it. So you hope that it's some shade of gray, basically, okay? Light shade of gray or heavy shade of gray. And as was just shown, it spans currently a gigantic set of masses over which it can exist. Thermal WIMPs refers to this WIMP miracle, whereby you could have something which is in the GeV region. Something like from 100 MeV all the way to something like 100 GeV, and explains the current observed density of dark matter in the universe. Now, on this, two takeaway messages is with respect to what you saw in the earlier talk. is that you create dark matter, for example, by making 2 charginos over here. The most powerful search that can reach, that can make us flip over the limit which is needed in order to get to the thermal limit for the WIMP miracle, is to create 2 charginos that go into a pion in the Kuiper 0. This is basically the kink and track or disappearing track if this pion is too soft. The other thing, of course, is through loops, whereby you, from your observables, you compare them to theory and you get limits. In both cases, again, this is the ultimate. This is 1.1 here for a pure Higgsino and 3 TeV almost for the pure Vino. And in both cases, the Hadron program would actually get to them. Now, one important thing is that the Higgs may also be a portal to the dark matter sector. We always say, we speak of the complementarity of searches. These are the direct searches that you just saw from Cybrand. These are the limits that you get in the spin-dependent case from the colliders. This is cross-section, this is a mass. Actually, if people say, it's good that this covers this region over here, and then these guys, the direct guys, cover this region over here. I think that it would be the ideal scenario would be that dark matter lies somewhere here, whereby you can actually observe it both with direct detection experiment, with astrophysics experiments, and with collider experiments. That would actually be the dream scenario if nature is actually kind to us. And the same thing holds true also if for the Higgs portal. The limits here from the collider look funny because, they go up to mass Higgs over 2, and then, of course, they disappear. Going on to... Sorry? Point there? No. It just refuses to cooperate. Oh boy. Is there any way I can do this physically with a keyboard? Like go boom, boom, boom? I'm pretty good at it. Now it's, I didn't flip backwards, that for sure, I can tell you that. I only keep going forward. No keyboard. As is well known, one of the major problems of today is energy supply. So. Is it, or just magic hands? Okay, let me, since we lost quite a bit of time, let me go into the other big chapter, which is the physics of flavor, neutrinos, quarks, and charged leptons. Neutrinos. Remember where it all started, from basically desperation. In the days of Pontecorvo, that basically took a cross-section of 10 to the minus 44 centimeter squared, at an energy of something like 2 MeV, and thinking that you could have a few events per day per ton with 10 to the 11 neutrinos per square centimeter. We're now at the level of doing actually mixing experiments. Mixing experiments are simple. Neutrinos are born and die as weak eigenstates. In between, they travel as eigenstates of the Hamiltonian, so they go as a mass eigenstates. And as a result, if you look at the probability for nu A to go into nu B, it's a mixing parameter and then something that depends on the mass squared, sine squared of delta M squared. And neutrinos have had 3 lucky strikes in their lives after this disastrous low cross-section. The first one is that the observation here of Super K and Snow meant that we have large mixing, very good delta M, so a delta M squared from solar neutrinos of almost 10 to the minus 4 eV squared. If you translate that into better units, it's something like an MeV over 100 kilometers. So that means you can actually do experiments at reactors. Then the other lucky strike comes from experiments, first IMB, Kamiokande, Sudan 2, there's a whole series of things and so on, which is atmospheric neutrinos and accelerated disappearance, whereby the delta M squared is 20 times smaller here. It's 2.5 10 to the minus 3. It's something like an MeV over 100 meters. And that means you can actually do it at accelerators. That was the second major lucky strike. Parametrizing it, you know that the equivalent of the CKM matrix, the PMNS matrix, breaks into three. One is atmospheric, the other one is short baseline reactor and atmospheric, and the final one is solar and Camland. Now, with this, there was a third lucky strike, which is the angle theta 1,3 turned out to be large. And why is this an incredibly lucky? This is thanks to this incredible observation of theta 1,3 in China, whereby theta 1,3, if you measure, if we take the magnitude of the total CP violation in the standard model, the so-called Yarskog determinant, it's proportional to these elements squared. At the end of the day, it turns out to be 3% times sine of delta CP. This is to be in the lepton sector. This is to be compared with the quark sector, where this value is 310 to the minus 5. So this is a much more prevalent phenomenon. If this sine delta CP is a large number, and incredibly enough, there are hints that it might be around 3 pi halves, so it means that the sine here is maximal, that would be very large CP violation in the leptonic sector. Now, where are we today? A long series of measurements have brought us into the precision era. If you look at all the delta M squares and all the mixing parameters sine squared thetas, they're at the level of 3 to 5%. This is the picture today. What comes in the future? Well, the ultimate prize, as we said, the CP violation. CP violation is actually a very complicated thing, because it's not just a matter of observing here the difference between matter and antimatter and so on, because these neutrinos in these long baseline experiments, they travel through hundreds of kilometers of soil and so on and so on. So actually, if you look at all the contributions that feed into one specific mixing, you see that it's the sum of all of these guys over here, which is why it's extremely important to have, oh my God, time is running out, which is why it's extremely important to have two sets of experiments at different distances. And we have the 200 kilometers in Japan and the 1,300 kilometers of dune. Bottom line here is that you can get a 5 sigma observation of CP violation within something like 6 years, 5-6 years after the start of these two experiments, Hyper-K or dune. Majorana, Dirac, and so on, covered by the previous talk. What about the quark sector? Quark sector, well, we have the CKM matrix. It gives you 9 equations. 6 of those equations correspond to triangles. The other 3 are just the diagonals. Of the triangles, they're all elongated, so it's horrible. CP violation is a small effect, except in the B system, where the 3 sides are roughly equal to each other, which is why B physics is ideal. Now, this is the infamous CKM triangle. As it appears today, as it will be in 2025, and as it will be in the year 2035. There's a very fertile program here of CP measurements, measuring the angle gamma also, to feed all of this. Recently, there is a lot of talk about potential lepton flavor violation, universality violation that comes from the B system. It comes from rare decays, and this diagram, B that goes into S, and it radiates a lepton plus, lepton minus. You could not have the lepton plus, lepton minus come from a Z directly off of here, because that would be a flavor-changing neutral current. It only occurs through loops. It turns out that if you compare how often this goes into electrons or muons, and in the standard model, as you can see, the two are an electroweak vertex, so they should be identical, modulo mass. It should be 1. Instead, it's off from 1. It's at 0.85 plus or minus 0.05. It's off by 3 sigma. There's a lot of attention that's been drawn into this, and perhaps you've seen it in the news. If you try to combine all the different anomalies from the B sector, what you get is this picture over here. This is a global fit in the context of effective field theories, the Wilson operators, and all of that. This is a standard model, And this is two sets of measurements, because this is now trying to combine both semi-leptonic decays, where also there is a bit of a disagreement, and this, these rare decays where you have this 3 sigma effect. If you concentrate only on the rare decays, what you have is a more consistent picture and still a large distance with respect to the standard model. This is very promising, and this is something that will be settled over the next 5 years, both in the upcoming LHC runs and in the at Bell in Japan. Kaons, extremely important because we finally have it in the pocket. It's a K plus that goes into K plus and nu bar. It's been seen by NA62 at Cern. Look at this branching ratio. It's 10 to the minus 10. This is just incredible. Okay, so this 15 events seen represents a tour de force for the specific experiment. If you look at the ultimate future, which is the charged mode versus the neutral mode is even tougher because it's the one that's called nothing in, nothing out, because the K long goes in, you don't see it, the pi 0 goes out, you don't see it. So there was some excitement way back from the Koto experiment, but that has subsided because they found that one event was fake, and then the background estimation went up by a factor 3. In the future, we hope to cover this area over here with respect to the standard model. This is if the central values stay the same. If you can also do flavor changing neutral currents with Higgs decays, and there are various limits that you can get from the various colliders. So it's also something quite rich. Finally, let me tell you about the last disagreement that currently exists is the muon G minus 2. There's a recent measurement from the Tevatron. It's come out, and to make a long story short, this is G minus 2. This is the old BNL result. This is the new Fermilab result. Same error bar. They are in agreement with each other, which is great news because everybody was afraid that the original distance between the Brookhaven experiment and the theory, which is the green line over here, was basically an experimental issue. It's not, because this is a completely different experiment, different systematics, and they agree. The total distance now between the average of the two and standard model is 4 sigma. On the other hand, this theory here comes from low energy data. And there's the biggest uncertainty, and this incredible set of calculations comes from the hadron vacuum polarization diagrams, whereby you can only use lattice QCD or the low energy EE data to actually probe that region. If you use lattice QCD, there is this measurement that's come recently here, and it has caused a lot of stir. This is the let's call them low energy data extrapolation theory, and this is the experimental result, and this one sits smack in the middle. Important news here is that we get already a factor 2 from Tevatron. So that's it. Pseudo summary and outlook. There's an extremely rich physics program ahead to understand the scalar sector. The LHC and high luminosity LHC will get us to 3 to 5%. All options for a Higgs factory yield a per mil. Important aspects, electroweak precision observables are the game of the next Z factory, and it's extremely important. And we can probe the Higgs and its naturalness to a very, very good level. Dark matter, we can probe a thermal WIMP. As for flavor physics, neutrinos is the next big thing, and we hope that we will get to CCP violation if we're lucky. As for the anomalies, we will know a lot more about the B flavor anomalies over the next 5 years. It is the best of times, as long as very soon, there is some kind of international move towards a new collider. At which point, what we really have ahead of us is all of what you saw here. Okay. Sorry for all the mess and losing my
Thank
stream.
you very much. I think it's very difficult to give a course of particle physics in half an hour. Thank you very much. So I think we will not have time for any question, at least something is extremely hot. So I would like to call the new speaker, Gerda Neyens from KU Leuven in Belgium, and he will talk about highlights and challenges in nuclear physics. I wish you keep the time, Gerda.
I'll do my best. Thank you.
Okay, so let's switch over to nuclear physics, some recent highlights. So I'll start with giving a brief introduction on what are we studying in nuclear physics, and then show some recent progress in nuclear theory and experiments, showing a few of the highlights from the last few years since our last meeting. And I'll finish with some outlook and perspectives and conclusions. So nuclear physics, the goal, of course, is to understand and unraveling the fundamental properties of nuclei from their basic constituents, and as well as to investigate the properties of the strong and the weak interaction and when they are at work in the nuclear medium, and in particular in the heavy elements where electromagnetic interaction is competing with these two. Okay, so this is the nuclear chart, and as you can see, the drip lines are indicated with the colored lines from different nuclear theories, whereas the proton drip line is quite well defined, both experimentally and theoretically. In the neutron drip line is very far away from the region of the known isotopes, which are the green isotopes, and the theory predictions are very diverse. However, knowing this area of nuclei is very important, for example, for the astrophysical processes leading to the production of the elements. So therefore, we are performing experiments to understand the nucleon properties better, and we do that in three extremes. As a function of isospin, so going to most neutron-rich and proton-rich isotopes, we see that, for example, in erbium, this is just an example, the neutron drip line is predicted to occur between 154 and 162 neutrons away, where experimentally we are now at neutron number 112, so still very far away. Second extreme is excitation, spin and deformation. And the third one is excitation energy, which makes the link to hadron physics. And you'll hear more about that also in other talks this week. All of our research is very much related to other fields, such as nuclear astrophysics and nucleosynthesis, which is covered in some of the presentations this week, as well as fundamental interaction studies and symmetries, also covered in some of the talks. But also techniques we are using are related to atomic physics and chemistry, for example, related to the production and the study of the heavy element region, and also very much to society, in particular with the production of medical isotopes. So regarding nuclear theory, the goal is to understand how are nuclei made, and therefore we start from the basic constituents, which are the quarks and the gluons. So nuclear physics is in the higher end of the mass region. So starting from QCD and effective field theories, it's now possible to derive nuclear interactions starting from the basic ingredients, and through ab initio calculations make predictions for the properties of nuclei in the nuclear chart. However, when we come to the more heavier nuclei, we have to use different methods, theoretical methods, to be able to solve the Schrödinger equation, which has led to different techniques such as configuration, interaction, and density functional theory. So currently, the application domain of nuclear theories is very diverse and also very wide. So at the upper end of the nuclear chart, we are still now using mostly density functional theories, because theories such as configuration interaction methods, which is mostly known as the shell model, are nowadays possible also already for quite heavy nuclei up to the lead region, which was done recently. But if we go to the lower end of the nuclear chart, there is where we can really do the calculations ab initio, starting from the fundamental ingredients and including all the observables, all the ingredients. And there we go. Okay, so ab initio nuclear theories have made a huge progress in the last years due due to two reasons, and one of them is mostly that there's been a development of a variety of quantum many-body methods to solve the Schrödinger equation on one hand, and then on the other hand, the possibility to derive the nucleon-nucleon interactions from QCD through higher effective field theories. As shown in this graph, they have made a huge progress in making calculations for heavier and heavier nuclei. And nowadays, it's possible to make calculations, which is called ab initio type, up to the thin mass region. And just an example to show that is a recent study that is going to be published soon, which is the study of the nuclear moments of isotopes just below 10, the indium isotopes, which have been studied up to the magic nuclear number 82, and which has been calculated here using coupled cluster using in medium SRG calculations, starting from chiral interactions and a bare magnetic operator derived fully self-consistently. And the calculations are the ones here in orange to be compared to the red data. So while they do not yet agree with the data in absolute values, they do reproduce the trend, and I think it's a very promising step forward for this kind of calculations. But also, as we are in the heavy mass region or mid-mass region here already, the data were compared to density functional calculations, which now are reaching spectroscopic accuracy. So now it's possible to calculate nuclear moments, which are fundamental properties of nuclei, using density functional theory for odd-Z isotopes, even and odd and odd isotopes, by including time symmetry breaking contributions to the mean field. And this allows to have an almost perfect reproduction of the nuclear moments. So another breakthrough is that ab initio calculations now are able to predict the drip lines of the nuclear chart. Here you see an example where calculations were done up to mass, up to Z equals 26, so iron. And note that experimentally the neutron drip line is known only up to the element neon, so Z equals 10. And that was achieved recently, and I will show the result at RIKEN in Japan. For the proton drip line, experimentally it's known up to much heavier isotopes, but unfortunately the ab initio calculations can't reach that far yet. So, on the experimental side, I'm going to flash some examples from experiments that were performed at a variety of facilities, and I'm running in the same problem, so there's something that we should push here. Okay, and I'll go through the nuclear chart from the heaviest to the lightest element. So starting on the heaviest side, let's look at the heaviest island of stability that's been predicted to exist theoretically, and that was predicted to occur around element with Z equals 114. At GSI, some experiments were done recently at the Tasca-Recall separator, where it was shown that the observations they had, discovery of a new isotope with a sequence of alpha decay energies crossing the Z equals 14 shell gap, as well as the discovery of a 0+ state establishing the existence of shape coexistence, that compared to theory allowed them to conclude that the center of this island of stability, which was predicted to occur around this mass number, is not consistent with this data. So it looks like it will have to be looked for in heavier, so new element regions. The terra incognita around lead 208 has been studied also recently. That means lead 208 is doubly magic and stable. So why terra incognita? It's the region southeast of lead, which is very neutron rich and for which little information is known up to date. So recently there was an experiment that was able to use an accelerated mercury beam 206 mercury to study the single particle properties in 207 lead. And through these nucleon orbits, which were established here for the first time, it's possible to make predictions in combination with theory on what's the last bound neutron, in which isotope it occurs, the 126 last neutron. And that occurs in the region of the astrophysical arc process. I'm not going to use the pointer because I have an impression that the problem is linked with that, which is a pity. But so the arc process is the blue line on the graph. And and there we go again. So going down in the nuclear chart further, we come in the tin region, and we come to the doubly magic 100 tin, which is a self-conjugate nucleus having the same number of protons and neutrons. And here there's a few experiments I want to highlight. One that was performed at Riken, and that was already mentioned at the last Jenas meeting, but I'd like to come back to it because of a new measurement that was done on the masses of the indium isotopes, and that has some consequences related to these previous meetings, as well as a new measurement of the charge radius of silver, which will add some complementary view on better understanding what is the structure of tin 100. So beta decay of tin 100 was studied at Riken, and the new result that was achieved was in agreement with extrapolations from the past. And these also are nowadays able to be calculated using these ab initio coupled cluster calculations with interactions derived from effective field theory. Now, the calculations fall somewhere in the middle between an old measurement that was performed at GSI. In fact, there were two such measurements, which is the blue bar, and the new measurement, which is the green bar in the theory curve. So the theory values, which are the full symbols, are in agreement somehow in between the two. So there's no real conclusion there. But it's also important to mention that this kind of calculations are important for the impact for neutrinoless double beta decay. Now, why I'm mentioning the result is because there was recently a mass measurement of indium-99 and indium-100, which is just below the tin 100. And in combination with the masses that were measured and the Q values that were measured in the experiment at Riken and previously at GSI, it is possible to make a new prediction for a better mass prediction for tin 100 itself. And it turns out that when doing so, the blue line and the red line in the lower figure are the calculated, extrapolated mass values for tin 100. And it turns out that the value from the Riken result kind of deviates from the trend, which makes the authors from the paper to conclude that maybe there should be a new measurement made to further confirm this result. Another type of experiments that can be done to shed light on what's happening with the structure in the region is to measure the charge radii of the isotopes. And such a measurement was done at Jyväskylä, trying to measure a very exotic isotope, 96 silver, by combining two high-precision techniques. And they were able to extend the measurements down to Z equals 50, measuring for the first time the charge radius of an isotope near tin 100 crossing the N equals 50 shell gap. And a rather unexpected result was obtained, being an increase in the charge radius, which at the present is not reproduced by any of the theories. So here they compared to density functional theories, which usually are quite good in reproducing the charge radii of isotopes all across the nuclear chart, but this sudden increase there is not observed, and so I think also here more experiments are needed to investigate this further. Further along the N equals Z line, going further down, I would say, we can investigate a property of the nuclear interaction, which is the pairing correlations. And in particular, along the N equals Z line, we can look at proton-neutron correlations, which are very strong there because the protons and the neutrons are occupying the same quantum orbits. And in particular, the isoscalar pairing correlation is something which is looked for. And here is the results from an experiment done at Ganil using the Agata gamma ray spectrometer, which allowed to study the excitation spectrum of ruthenium-88, having 44 protons and 44 neutrons, up to very high excitation energies. And comparison to theory showed that isoscalar proton-neutron pairing is very strong in this region, where the nuclei are also very deformed. So now I move to isotope shifts, measurements, hyperfine structures, and charge radii, which are a rich source for to get information on the nuclear structure, both for nuclear structure studies such as they are sensitive to shell gaps, deformation, neutron skins, as well as related to particle physics studies, as recently there's been a few papers claiming that there's also the possibility to search for new bosons, and also charge radii, hyperfine structures and isotope shifts can be sensitive to anomalous nuclear moments such as the anapole moment and the shift moment. Now, first about the isotope shifts and the sensitivity to the existence of possibly a new boson. So this was presented in 2 papers recently where studies were done, high-precision studies of isotope shifts in stable isotopes of ytterbium and calcium, whereas it was claimed in the paper on ytterbium that the nonlinearity observed in the King plot, which is the deviation of the experimental data points, which are highlighted there in blue, from the straight line that is expected, would be an indication that there is some physics beyond the standard model. And in the paper, they explain it as the possible existence of a candidate for dark matter. However, it could also arise from higher order nuclear effects within the standard model. A similar analysis of data on stable calcium isotopes did not reveal such a deviation, so it's clear that more data on this are needed to make a conclusion on that. And here radioactive ion beam facilities where plenty of isotopes are produced and we can study the isotope shifts of very long chains of isotopes could be looked at in the future. Note that the precision of the studies on the stable isotopes currently of the order of sub-kilohertz, so the ytterbium was 0.3 kilohertz, the other one an order of magnitude even better, while currently at radioactive beam facilities the precision is typically of the order of a few hundred kilohertz. So we are still a bit far away from that. As said, the charge radius is also an observable that can be used to constrain other parameters such as the neutron skin in nickel-68. And that's because ab initio nuclear theories have shown that there's a strong correlation between, for example, the dipole polarizability of isotopes and their charge radius. Here shown in the graph, you see on the x-axis, on the y-axis, the dipole polarizability, and on the x-axis, the charge radius. The crosses are the calculations using different chiral interactions with coupled cluster calculations, including error bars on the theories. And the green line and the black line are the experimental data for the charge radius and the dipole polarizability. And it's clear that from the calculations that three-hole correlations were needed to include in the theory in order to get a better agreement with the experimental data. So these are also possibilities, and also through that it was possible to constrain on the neutron radius and the neutron skin of nickel-68. Another charge radius measurement that was done recently was the charge radii of isotopes just below calcium, which were shown at the last meeting. Here, the charge radii of potassium have been extended beyond the new neutron magic number n equals 32, for which the result was that there was no special behavior observed in the charge radii. It's a smooth trend up until n equals 33, which is well reproduced by density functional calculations. So the trend, at least at the steep increase, is well reproduced, but the staggering is a little bit overestimated. But still, ab initio coupled cluster calculations cannot reproduce the steep observed increase in the charge radius. Going down in the nuclear chart further, we arrive in the region of fluorine and neon, where, as I said, the drip line has now been firmly established. For fluorine, it's at fluorine 31, and for neon, it's at neon 34. For sodium, it's not yet firmly established because one event was seen in sodium 39 in the lower plot on the right. So there, it's not yet sure where the drip line will occur. And as I showed before, these are important measurements to test the predictability and the reliability of the ab initio calculations, which agree very well with these new observations. In fluorine, there was also the observation of a new halo nucleus. Halo nuclei are known to exist already many decades now, and we have observed several of them, such as helium-6, lithium-11, beryllium-14, in boron and in carbon. Now, the next element in which such halo was observed is in fluorine, with an increased cross-section measurement performed at RIKEN for fluorine 29, which has 20 protons. So again, the result was compared to theories in the paper, and it was shown that the effective shell model interactions, which are more empirically based, are able to reproduce very well the observation of the large cross-section and the increased matter radius. However, again, the ab initio calculations are still not doing as good in making these calculations work fit to the theory, to the experiment. We reach almost the bottom end of the nuclear chart, and so here I want to show a result from PSI, where the alpha particle charge radius was measured using muonic helium. So when you add a muon to a helium atom and replacing an electron by a muon, you are much more sensitive to the nuclear charge radius because it's much closer to the nucleus. So using this technique, they were able to improve the measurement of the previous measurement of the charge radius by the factor of 5. And what was interesting was that the result was found to be in nice agreement with the electron-helium scattering experiments that were done at colliders, and also in agreement with the recent determinations of the proton charge radius. Furthermore, the result led to a 10 times improvement of the charge radii of the halo nuclei helium-6 and helium-8, and again provide a nice input to test modern nuclear theories. On the very bottom, we have the neutron, and the neutron is being studied also at PSI, where there's a collaboration to study the electric dipole moment in the neutron. And very recently, they've been able to improve the electric dipole moment sensitivity with almost a factor of 2 as compared to the previous best value, which was published in 2015. This was mostly because they could reduce the systematic error in their studies by almost a factor of 5. And there's a new measurement now in preparation, which is the N2 EDM experiment, which will be able to push the limit of the sensitivity to the EDM below the 10 to the minus 27 e centimeters squared. So, going from matter to antimatter, I think it's also important. And in antimatter physics, there's been a few recent highlights which will in the very near future allow to push the precision of matter-antimatter research and comparison even further than it is today. And that's related to the fact that it's been shown that laser cooling is possible of anti-hydrogen atoms, as well as cooling of antiprotons through the sympathetic cooling with laser-cooled beryllium ions. That was done at 2 collaborations at the antiproton factory at Cern, where they will be able to push the sensitivity of laser spectroscopy to much higher precision. They could currently improve with a factor of 4, and the sympathetic cooling with the beryllium ions will also be able to push the precision of the antimatter-matter comparisons in the near future. However, even without that, the base collaboration has been able, and now it's stuck, right, to improve further on the precision of the ratio between the charge and the mass of antiprotons compared to protons. They've pushed the precision another factor of 4 better than their previous best value, and they've now shown that within 16 parts in a trillion, the ratio of the charge to mass of protons and antiprotons are exactly the same. And this is fully consistent with the fundamental charge parity time reversal invariance in the standard model. So, as an outlook and perspectives, I'll just give you some limited selection of future experiments that I think will be performed in the near future, and that's the use of radioactive molecules as a probe for new physics, the use of hypernuclei as new probes to test nuclear models, and the thorium isomer, which could potentially be a new standard for time, but also be a new way to probe fundamental constants. There's a lot of topics I couldn't cover in my talk within the given time limit. For example, the link to neutrino double beta decay, which I mentioned, which is very important for through measurements that are done in nuclear physics, but also through the theory input that is needed for these type of experiments. Also, the search for CP violation and the weak currents in precision beta decay, which is strongly linked, of course, to the search for that we just heard in the previous talk, as well as the nuclear physics aspects, which are related to nuclear astrophysics, neutron star mergers, and gravitational waves. So, just let me give an outlook to the radioactive molecules. So, if you look at the plot here, which shows the measurements of electric dipole moments, initially they were done mostly in atoms up until, let's say, the beginning of this century. And then suddenly molecules took over the field, and the highest precision was achieved in molecules like ytterbium fluoride, hafnium fluoride, thorium oxide. And what's typical about these molecules is why are they more sensitive is because the electric fields in the molecules are larger than in atoms. However, there's another parameter or a few other parameters that can make a molecule more sensitive to such electric dipole moments, and that's on the one hand the Z of the nuclei in the elements in the molecule. So the higher the Z, the more sensitive. That's, for example, why thorium oxide was a very sensitive molecule, and also radium would be radium fluoride would be a very sensitive molecule. Another observable that makes a molecule more sensitive, but also an atom, is when it has an octupole shape, so when it's pear-shaped. And radium molecules are pear-shaped. Now, radium fluoride has not been used so far for such studies because radium has only radioactive elements, so it's not so obvious to study its spectroscopy. Just an intermezzo, we know that radium isotopes, at least 5 of them, are pear-shaped because they've been studied at Isolde at Cern, where it was shown that radium-222 to 226 have a static pear shape, while some of the other isotopes in the region are vibrating pears. So it makes that some of these isotopes are sensitive to these electric dipole moment studies. So, thanks to the first spectroscopy that we could perform on radioactive radium fluoride isotopes, we now have the tools to go for the next step, to go for the precision studies. And the other nice feature that was seen in these experiments is that all the conditions are present to allow for laser cooling, which is also an important prerequisite to go for higher precision measurements. And I'm almost at the last slide, 2 to go. So, as I said, exotic neutron-rich hypernuclei could be an alternative way to test different theories, including nuclear theories. Some pilot experiments were done at GSI already a decade ago almost, but recently there's been a new experiment installed at the FRS, which is the WASA experiment, and some first experiments were performed just a few months ago in preparation of doing such experiments at the Super FRS at FAIR in the future. So this will provide a new tool to look into nuclear and let's say, the structure of binding hadrons. And my last slide is another topic that was discussed also last year, 3 years ago, and that's the search for the properties of the thorium-229 isomer, which is a very particular isomer in the whole nuclear chart because it has an excitation energy of only about 8 electron volts. And 8 electron volt is an energy you can reach with lasers. So if you could excite this isomer with lasers, which you can do if you can make a laser with the proper wavelength, and this we can do, but also if you know, of course, which wavelength to use, then this could have a lot of applications. For example, it would be possible to make a nuclear clock which is about 10 times more precise than the current atomic clocks. However, before we are there, there's a lot of work to do, but I think a breakthrough has been made just a few months ago because the first step, of course, is to know which energy is needed, which wavelength is needed for the laser, and the current precision was 3 nanometer uncertainty on a value of about 150 to 153 nanometer, which would mean you would have to search for or scan for at most a year or almost a year to eventually find a resonant excitation. Now the energy has been improved by a factor of 5 to 10, and I think in the next experiments another factor of 3 to 4 could be reached, such that it's possible in the near future to start searching for a direct excitation of this isomer with lasers in just a month's research. So my conclusions: ab initio models as well as density functional theories are progressing very fast, and of course with ab initio models I also mean all the quantum many-body theories that have been developed, coupled cluster, shell model, in medium SRG, etc. They have made a very fast move forward, both in predictability of the nuclear properties, which, as I said, are also relevant for other fields. There are several new upcoming facilities that will allow us to explore further the limits and to get new regions of the nuclear chart. And I think I've shown that nuclear physics is a very multifaceted area, reaching out to different disciplines. And finally, it looks like precision measurements are becoming more and more important to make the links also to other fields, which are here in the audience: particle physics and fundamental symmetry studies. Thanks.
Thank you very much. Thank you, Gerda. So any quick question before coffee? No, I think. No, everybody's eager to have coffee. So thank you, Gerda, and thank you all the speakers of this session.
Okay, so welcome back to the second session of today. This is the session on overall strategies, and we will hear 3 talks from the 3 communities. And we start with APEC. Andreas, Hans, please, your turn.
Yeah, thank you very much. Talk has still to be loaded. Yeah, okay, it's a pleasure here to discuss a little bit more in detail the strategy which we follow in astroparticle physics, mainly driven by APEC. And this is not only a European view, but also a view from APEC, what we are doing and plan to do in the next periods. So first, what is astroparticle physics? It is the understanding the multi-messenger and the dark universe. Astroparticle physics is a branch of fundamental science embedded in environment and society. And who is an astroparticle physicist? And here I like very much the definition in Wikipedia, which writes, while it may be difficult to decide on a standard textbook description of the field of astroparticle physics, the field can be characterized by the topics of research that are actively being pursued. So this is somehow everybody who feels he is an astroparticle physicist is an astroparticle physicist. And this is also somehow the motivation why we have it here in this Jenas Symposium and discussing synergies and overlaps and what we can do together. So APEC is an astroparticle physics European consortium. You see here the member. It's an international coordinating structure. It was funded in 2012, so it's relatively young, like the field. It is based on Memorandum of Understanding, and it is a financial agreement with DESI as a host of the APEC Common Fund, because astroparticle physics does not have a global center. We have distributed experiments all over the globe. And we have, at the moment, 17 member countries, 21 funding agencies, and 6 observers, and also a small budget to support such meetings like here, the Jenas Symposium. The bodies of APEC are the General Assembly, the Scientific Advisory Committee, a Joint Secretariat, and we have also observers. And here, of course, also our colleagues from ECFA and NUPEC here are contributors to the APEC activities. So what are the activities? We try to guarantee coordination of European astroparticle physics between funding agencies and visibility at ministry level through a lot of measures. And today I would like to concentrate here a little bit on the road mapping. So this is our main task, to develop and update roadmaps based on scientific strategies and financial considerations. But of course, you see it here, we have many other tasks and issues to follow. The APEC strategy process is foreseen to help in coordination of the large-scale research infrastructures, but there are, of course, also in the field mid-scale experiments where we want to help in transition from these mid-scale experiments, often national mid-scale experiments, to large-scale research infrastructures. And also, we do not forget the smaller scale and small-scale experiments, which are mainly used as R&D for the next generation of the large-scale research infrastructures. So, of course, I cannot cover here in this 25 minutes everything what we are doing and what is the strategy of astroparticle physics. That means I will focus on main considerations from point of view of APEC, and I will focus on the flagship, on the future flagship experiments or facilities whose main contribution lies in the field of European astroparticle physics. So this is my task today. Okay, so APEC roadmaps, we have submitted or distributed our first roadmap in 2008. Then in 2011, we made an update to this roadmap. And in 2017, we published the European Astroparticle Physics Strategy 2017 to 2026. What we are currently doing is, in this roadmap, we have scientific topics. And what you see here in blue, in lighter blue, are the topics which I will go a little bit more in details, and where we foster large-scale research infrastructures. And there we have also some organizational and societal issues related. Not only the scientific issues are considered, but also something like how we deal with European Commission, how we have, and this is Jenas again, interdisciplinary opportunities, and in particular, this block here is a topic which we also want to discuss with the funding agencies on Thursday. Things like gender balance, education and outreach, but of course also Detector R&D, open science, citizen science, and the ecological impact and industry of all our research. So as I said, what we are doing now currently is a midterm evaluation of the roadmap. Seibrand has discussed this a little bit. And the reasons are described here on this slide. It is and this is coming from this roadmap 2017, where you see two colors. You see the darker and brighter colors, the lighter colors. And the darker colors also show the costs for the maintenance and operation of the research infrastructures. This is always getting more and more important, that one consider for such infrastructures the costs also of the maintenance and operation, in most cases over many, many years or even decades. So what is a midterm evaluation? The preparation of a roadmap update. And there we had not only this discussion in the scientific advisory groups, but also specific topics and subcommittees which has considered the actual status and the future of dark matter, of double beta decay, and we will have a detailed multi-messenger discussion workshop later this year. So what are the goals of this evaluation? It is identification of new developments and new topics. We have to update the recommendations in the roadmap, and we have to update the time and cost line. In end of 2021, we distributed already this evaluation to the community and or to the national communities, and we got a lot of feedback. This was implemented in the evaluation, and now we will have a town meeting in June where we will discuss this feedback together with the communities in order to find the right words and the right topics for the update of the roadmap. So let me go a little bit into the details of these experiments and research infrastructures. First topic is a multi-messenger astroparticle physics. It is required to have multi-messenger astroparticle physics to understand the sources of cosmic rays and the physics processes in the high-energy universe. This needs long-term operational observatories. They are, because of the type of what we want to measure, they are distributed over the globe and mainly also on some strange environments. And what we also need for this is a sophisticated big data. You cannot combine data from different observatories if you do not take care on the management of the data. This means big data analytics, research data management, data curation, and also open data in order to foster this multi-messenger astroparticle physics. This is a very important topic here. First, let's come to the high-energy gamma rays. So there's one slide now, so to say, on the status. You have heard by Seibrand that it covers a large energy range with different observatories. We have satellites, we have imaging air Cherenkov telescopes. There are ground-based arrays for the higher energy gamma rays. And the main future project where APEC is somehow responsible, where it's directly in the European astroparticle physics funding, let's say, is of course CTA, which is an S3 project. So this is a nice picture of CTA, how it will look like in the near future. And here's one slide with the status. There's a rich science program, and all these experiments, which I will show, are not only dedicated to one scientific topic, they are also have a variation of scientific issues, which are also of interest, of course, for the neighboring fields. As I said, it is an S3 project. It will be an open, proposal-driven observatory. So this is the first one in astroparticle physics, coming closer to astronomy. 3 telescope types, small, large, and medium-sized telescopes. It will be at 2 sites. The governance will be in ERIC, and it consists of 31 countries, more than 200 institutes, and 1,400 scientists. So it's already coming very close to the big particle physics experiments. And the construction will happen in the next 3 to 5 years. That means in principle it is funded. Let's go to high energy neutrino astronomy, where IceCube opened in 2013 the new window with larger than 100 TeV neutrino astronomy. Also here we have several experiments which are now organized in the global neutrino network. It is IceCube, which will go to IceCube Gen 2. It is Antares, which will go to KM3net, and we have Baikal GVD. There are also some R&D phase, in particular for the highest energy neutrinos, the cosmogenic neutrinos. Here in the spectrum, it is here the upper end. And there are several experiments here which are trying to find these highest energy. This is based on radio measurements of air showers, and or from space like Poema. The European flagship is again a S3 project, which is KM3net, but there's also a strong partner. We are strong partners in Europe of the US-led IceCube Gen 2. Here's a picture of the KM3net experiment. And here are a slide to the status. As said, it's a S3 project. KM3net consists of ICA and OICA. This was explained by Seibrand. There's this discovery and subsequent observation of neutrino sources, determination of mass ordering of neutrinos by OICA. ICA is a high-energy neutrino astronomy. It's at the Italian site. Installation started. It will be completed in 2026. OICA is a low-energy neutrino physics facility at the French site. Installation started. It should be completed in 2024. 15 countries, more than 250 scientists are involved. And the third messenger is a high-energy cosmic rays. And here it is important to find, as Seibrand explained, where is the transition energy range from galactic cosmic rays to extragalactic cosmic rays. We have to understand the hadronic interaction models at these very high energies here. Composition, anisotropy, suppression mechanism. And here the Pierre-Auger experiment is a major experiment. We have some extensions, which is called Auger Prime, and there's also extension of the North American telescope array, which will be increased by a factor 4 in area. At lower energies, we have the LASO experiment in China, and also IceCube Gen 2 is sensitive to cosmic rays in the PeV energy range. And there are some future projects like Poema from space, Grant, the radio array in China, which Seibrand has discussed, and also TCOS, which means the global distributed cosmic ray experiment, where we also have some concepts and some idea to have it global, cost-effective, sustainable, to perform this experiment in a sustainable way. This is a picture of the Pierre-Auger Observatory. And the status is that we have Auger upgrade to Auger prime. It is will complete the construction in 2023, and then there is foreseen operation time until in the 2030s. And Auger will also be used as an R&D site for the next generation experiments, maybe at the end of the 2030s, or if we are lucky, in the middle of the 2030s. Oops. Gravitational wave detection. No, that was fast. Okay. Gravitational waves I want to discuss is, you all know that the first detection was in 2015 by LIGO and Virgo, in 2022 plus, so now in the coming years there will be a data taking with advanced LIGO and advanced Virgo, which will increase the volume of the visible space by a factor of 50. But then it is foreseen to go into the next generation, which is the Einstein telescope, where we will have an increase of the visible space by a factor of 1,000. There is a worldwide collaboration on these gravitational wave detectors, which are called QUIC and QUAC. The QUIC is a Gravitational Wave International Committee, so this is science, and the QUAC is a Gravitational Waves Agency's correspondence, and they meet regularly and discuss the future of the experiments. There is a gravitational wave ground space complementarity with the Einstein telescope and Cosmic Explorer at, you can see here, sensitivity of Einstein telescope. In the higher frequencies, in the lower frequencies, we have then the space experiment, LISA, before ELISA. And at the very low frequencies, one can use pulsar timing arrays and also, for example, the SKA. Here's a picture of the foreseen Einstein telescope with 3 arms, each 10 kilometers long. And this is a status of the gravitational wave detection of Einstein telescope. Again, we have an interdisciplinary science case. Many different topics can be treated here and investigated. The status is that there is a large interest in Europe on the Einstein telescope. The last large Einstein telescope symposium had 710 participants. It is now a S3 project. It was successful. It's now on the roadmap, and since June 2021. The organizational structure of the project and the collaboration has evolved. There are many boards have been formed: Instrument Science Board, Observational Science Board, Site Characterization, E-Infrastructure Board. And there is R&D, the Advanced Virgo, Advanced LIGO, CACRA, ET Pathfinder, and maybe also a new possibility to have an R&D site in Germany called Deutsches Zentrum für Astrophysik. Changing the topic now to dark matter. We have already seen in all 3 talks before that dark matter is a very interdisciplinary subject. It has a large overlap with the neighboring fields. And you see here the very large mass range, possible mass range with all the candidates. As I mentioned, there was a subcommittee report from APEC, and they have formulated 7 recommendations. And of course, dark matter search should have some priority. There's a diversified approach needed. The direct search for WIMPs down to neutrino floors, this was discussed by Seibrand. Coordinated detector R&D is important. European infrastructure for underground science is here a very important topic. And studying of the axion Alps mass range, continuation of diverse theoretical activity. So what is in our focus currently is the dark matter WIMP search with liquid xenons. There's also the recommendation to have with argon, but liquid xenon is quite enhanced now, and and studied. And the Darwin experiment will have a lot of possibilities, and showing here also the interdisciplinary science topics. The status of Darwin here is that APEC recommends to realize worldwide at least one Xenon and one argon experiment. Darwin is currently the European flagship experiment for the WIMP search. In addition, ongoing detector R&D has to be pursued. Xenon, Darwin, and Lux Zeppelin collaborations have signed a common MOU with more than 600 authors. And so we have to see what in the coming years, how it will develop here for this WIMP search with such a Xenon experiment. Anyhow, it will need a European infrastructure for underground science. This is a very important aspect here. And neutrino properties, again here, this was also discussed in the previous talks. The science here has a large overlap with neighboring fields. There are a long list of topics, what we do not know. Neutrino CP violation is still unknown. Neutrino mixing is very different from CKM. Neutrino nature is undetermined. Neutrino mass ordering not yet determined. Neutrino masses give access to higher mass scales. And neutrinos are the first hot dark particle and has a role in various stages of development of the universe. Again, the activities here needs a European underground infrastructure. I will pick one topic here because this is again going to a large research infrastructure. This is a neutrinoless double beta decay, where we go now towards a ton scale experiment. There are 4 candidates which were discussed: Qubit, Legend 1000, Nexo, and Next. And I want to show you a little bit the status here. There was many strategy discussions, and the status now is that the Double Beta Decay APEC subcommittee gave advice on the European and global program. It provides an assessment of the current and future scientific opportunities in double beta decay over the next 10 years. There's a close cooperation of APEC with DOE nuclear physics, and it's also aligned with the SNOMAS process. In spring 2021, we had a DOE portfolio review on neutrinoless double beta experiments. And in autumn last year, we had a European North American summit at Gran Sasso, Italy. So there was also a closed session of funding agencies with the result that neutrinoless double beta decay should have high priority. The funding agencies in Europe and North America should build a network, and if possible, Legend and Nexo should be funded, one located in Europe and one in North America. And this is the status, and now I summarize this here, the scientific APEC flagship research infrastructures, and you see here again the KM3net, OSHE Prime, CTA, and gravitational wave Einstein telescope, where this is more for high energy and dark universe, and this one for the high energy universe. Then the dark matter developments, and from our point of view, the neutrino properties currently focusing on Legend or on neutrinoless double beta decay experiment in the ton scale in Europe. As I said, in the roadmap, we have also overarching topics: ecological impact, societal impact, open science, human talent management. These are all very important things. Open data and citizen science, here's ESCAPE, to name it. We will have a talk, I think, on Thursday. Computing is an important topic, theory, and also the coordination of European underground labs. Most of these topics we will discuss also in the next couple of days within here in Jenas, because all these topics have a large overlap with the neighboring fields. Then one word to strategy connections. In the APEC strategy process, there are strong connections to ECFA, to NUPEC, to Astronet, to SNOMAS, and also to the Decadal Survey, Astro 2020, and of course also to the national communities. Let me show one slide to the APEC and the European Union framework programs. So APEC was indeed created in 2001 as a coordination instrument of the European agencies which funds astroparticle physics. It got a boost by European funding of the Aranet Aspera, that was in 2006 to 2012, so our first name was Aspera. Then in this frame, we could launch successful community-driven proposals like ILIAS or ETDS. Cooperation with ESCAPE, member of advisory board, like also ECFA and NUPEC. We also participate in current calls like Infratech with proposals like named Apogeia and M2Tech. And what is important is for the Horizon Europe work program 2023 to 2024, there is a call in InfraSurf where the scientific domains called under this topic are, among others, astronomy and astroparticle physics, so called in one line. So we have to come together with astronomy, with the European astronomy in order to write such a proposal, as it was happening in the last year with APEC and ECFA had to write a common proposal. We have also a technology platform, which is a platform for discussions and collaboration with other organizations and industry. It fosters also interdisciplinary R&D projects. And here just a little bit advertisement. The next tech forum is foreseen to be held in Prague in September this year, focusing on robotics and operation of detectors in harsh environment. And this, of course, can also be of interest for all neighboring fields. Coming back to the midterm evaluation, coming now close to the end. Midterm evaluation of the roadmap. We have a diverse program with requests to realize large infrastructures. We have a balanced plans for investments. General shift in schedule due to slow realizations. So when we built this in 2017, we have foreseen that in 2022 one should do an update because nowadays it is very difficult to find the money here in order to do this. That also, of course, the price tags have to be checked and updated. Societal and environmental impact, as well as economic and ecological footprint and sustainability are becoming more and more important for the next generation research infrastructures. And of course, one can always ask, is astroparticle physics or other research fields too expensive? One have to say, compared to what? So I believe that about 100 million per year, which you can see here, for operation and for investments from Europe, from the European funding agencies, for such an extensive research is relatively cost effective, I would say. And here again, the invitation to all of you to participate on the town meeting in June. So my summary, astroparticle physics is a booming and blooming field in search of wonders of the cosmos. We are going to understand the fundamental law of nature, and there are plenty of opportunities for young scientists. The next steps for APEC are the town meeting, which means a midterm evaluation and update of the roadmap in 2022, so this year. And of course, we always coordinate as European astroparticle physics in cooperation with the neighboring fields. And if you are interested, you can also have the APEC newsletter and APEC, and we all try to further foster and coordinate the European astroparticle physics. So thank you very much.
Okay, thank you very much for this very interesting talk. You kept very well the time, so we have time for 1 or 2 questions. So please, if you have questions to this interesting program. Yeah. There's one. This. 1 minute. 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 1 minute.
Thank you. You mentioned a number of times the need for new underground infrastructures and better cooperation between existing infrastructures. Can you say in a bit more detail what you think is required there?
I mean, we have in Europe, we have, of course, the Gran Laboratory as a large infrastructure where there is space for large experiments. There were in the current situation or in the current generation of these underground experiments, there are also in other, like Modan, Canfranc, Bolby, there are other experiments. But in most of these underground labs, there are problems to install, like in double beta decay, a ton scale experiment, just by space. But nevertheless, we need these laboratories to do the R&D, to go for the next step. And that means we need a coordination and we need support also from the national funding agencies that the support for these R&D steps. Which is not the final experiment. Of course, they should also have own experiments. But what we need is, so to say, a coordinated effort to reach efficiently the next generation experiments. And this is mainly related also to the edge technologies. That is not done at several places, and every lab has their advantages which should be used.
Thank you.
Okay, I propose we thank Andreas again and move on. Next is the presentation strategy of ECFA. Originally, it should have been given by Karl Jacobs, but he had to cancel his trip, I believe, yesterday. So we are very grateful to Patricia Conde Munio for accepting this challenge with such a short notice. Please, Patricia.
Okay, thank you. Yeah, so okay, so, well, I will present my interpretation of the slides from Karl on the European strategy of particle physics. So, and I have to thank Paris for the very nice presentation this morning, because this afternoon, because he will save me a bit of time in explanation and the motivation for this strategy. So you have seen already what we have been doing at the LHC in the last 10 years, and this has been the focus of our community. We have discovered this new state of particle, the Higgs boson, and but we have also measured its properties, like coupling to most of the fundamental particles. We have also performed precision tests of the standard model, such as the W mass measurement, top quark mass, and we are challenging with these measurements the standard model, in particular, for instance, in flavor physics, where we have these deviations that are not really in agreement with the standard model, but we are yet not at the 3.1 sigma level, for instance. In this case, this is a flavor. This is sorry? To change the slides. Okay. No, I was trying to point here. So lepton flavor universality violation, okay? We have also been pushing the limits of the searches for physics beyond the standard model at the TeV level. And last but not least, also the LHC is also a heavy ion collider, and we are exploring QCD in extreme conditions. So over the last 10 years, as you can see in the slide, we have performed a long list of measurements of standard model processes, covering a very large range of cross-section values. And this is a triumph of the experiment, but also of the theory, who had to push the calculations to match the precision of the experiment. And we have observed that the standard model provides a successful description of the data. However, as we saw, there is an increasing tension with the standard model in the flavor sector, and there are also many open questions we have not yet managed to solve. And these open questions cover several different areas. On the one hand, the Higgs sector, this unique particle we heard about today already. And questions such as why is the Higgs boson mass so light, and what is it connected to dark matter sector, to the hidden sector, and so on. So for this, our best opportunity is to explore the properties of this new particle with higher precision. So such that, well, this may be the key to understand the physics beyond the standard model. And the key word here is precision, so we have to go higher up in precision to probe really the predictions and be able to search for new physics in this sector. In addition, we have the flavor sector with many open questions. In addition to these tensions with the standard model, we also have questions such as why do we have 3 families? What is the origin of neutrino mass oscillations? We have also the question on dark matter. What is the origin of dark matter? And has come several times today. In cosmology and gravity, what is the cause of the accelerated expansion of the universe? Why is gravity so weak? What is the origin of the matter-antimatter asymmetry? So all these questions require new physics beyond the standard model. And however, at the moment, we have no clear indication what is the energy scale where we have to search for this new physics. And this is the place where the European strategy comes. So there was this upgrading in 2020 of the European strategy for particle physics. This is a process that takes 2 years and involves the whole community, aiming at developing a common vision for the future of particle physics in Europe. So this is a bottom-up approach, starting with a consultation to the particle physics community that provide, across universities, laboratory, national institutes, and research centers that are invited to submit written input by, in this case, by the 18th of December 2018. Then there was, this was followed by a scientific open symposium in Granada in May 2019, where the community was invited to debate the future strategy in the European particle physics. This symposium was followed by a briefing book, by a session dedicated to writing a briefing book in Bad Honnef in Germany that happened in January in 2020. And the update of the strategy was finally presented and approved at the Cern Council in June 2020. So as recommendations from this strategy, there are several recommendations that come in this book, and one of the first and major important point is that the successful completion of the LHC program, including the high luminosity upgrade and also the machine and detector upgrades, and the exploitation of the physics reach of the high lumi LHC. Including also flavor physics and the quark gluon plasma, as mentioned before. In addition to that, Europe and Cern, through the Neutrino platform, should continue to support the long baseline experiments in Japan and the United States. In particularly, Europe should continue to collaborate with the United States and other international partners towards the successful implementation of long baseline neutrino facilities and the deep underground neutrino experiment, DUNE. There were also general considerations for the 2020 upgrade, and this is that Europe should continue carrying the world leadership in accelerator-based particle physics and related technologies. And the future of the field in Europe and beyond depends on continuing ability of Cern and its community to realize the compelling scientific projects. particle physics community must also further strengthen the unique ecosystem of the research centers in Europe, and cooperative programs between CERN and national research centers should be expanded and sustained with adequate resources in order to address the objectives set out at the strategy upgrade. Okay, the implementation of the strategy should proceed in a strong collaboration with global partners also in neighboring fields such as astroparticle and nuclear physics. Okay. In addition, there are these high priority future initiatives, and the electron-positron Higgs factory is the highest priority for the next collider. And, however, in the longer term, Europe, the European particle physics community has the ambition to operate proton-proton colliders at the highest achievable energy. And to accomplish these goals, will require both innovation and cutting-edge technology, and the particles physics community should ramp up its R&D effort, focused on advanced accelerator technologies, in particularly for high-field superconducting magnets, and including also high-temperature superconductors. Okay. Europe, together with its international partners, should investigate the technical and financial feasibility of a future hadron collider at CERN with a center of mass energy of at least 100 TeV, and this with the first step being an electron-positron Higgs factory, an electroweak factory also as first step. So, such feasibility study of the colliders and related infrastructure has to be established then in time for the next European strategy upgrade that will happen in 2025, after 2025. So the timely, in addition, there was this statement that the timely realization of the Electron-Positron International Collider, ILC, in Japan, would be compatible with this strategy. And in this case, the European particle physics community would wish to collaborate with that. Okay. So concerning the Higgs, the high energy plus and minus collider projects, there are currently 4 projects in the market. There are linear colliders such as ILC in Japan and CLIC at CERN, and circular colliders such as Future Circular Collider at CERN and the electron-positron collider in China. Okay, each of these has different characteristics, as you can see. So the linear colliders, they can reach higher in energy. They will go in phases, starting, for instance, ILC with 250 GeV, reaching 1,000 GeV in several years of operations. CLIC will start in 380 GeV and will go up to 3,000 GeV with different expected integrated luminosities. Okay. FCC or CEPC will accumulate much higher integrated luminosities while operating at lower energies. For instance, FCCE will go up to 2 times the top mass, while CEPC will operate at up to 240 GeV. And this is also seen in this plot where we can see that there is balancing between luminosity we can achieve and the center of mass energy. And so with circular colliders, so it's achieving much higher luminosities, while linear colliders will be the energy frontier. Here we can see also a comparison of what we can achieve, for instance, in FCC with the statistics for the precision area. In comparison with LEP, for instance, the number of set bosons will increase by a factor, by 6 orders of magnitude. For instance, WW bosons will, production will increase by a factor of, 4 orders of magnitude higher. In terms of the Higgs sector, we have already seen some previsions in the previous, in the presentation by Paris. We have here the Higgs coupling strength modifiers and the precision we can reach in probing these in FCC-EE, for instance, and we can go up to the, well, most of the cases % level, few % in some cases. While this is FCC-EE, for FCC-HH is something, well, below 1% level, but combining both of them, we can go back down up to 1 per million in some cases, okay? So the combination of all these machines and the flexibility that they allow, for instance, going to from different EE, HH, or allow to improve our reach in terms of physics. So we have to perform this feasibility study, and Cern, okay. This work has already started, and the organizational structure was already approved by Cern Council in June 2021. And they have identified the main deliverables and milestones of the study that has to be done. You see here, for instance, an image of the one possible location of this FCC machine in the Geneva region. This is the lake. It will go under the lake. Well, this is the Jura Mountains. This is Salève, and it will go around. So the major goals of this FCC feasibility study are, first of all, very important, optimization of the placement and the layout of the ring and the demonstration of the geological, technical, environmental, and administrative feasibility of the tunnel and the surface areas. This is quite important. In addition to that, we have to pursue together with the host states the preparatory administrative process that are required for a potential project approval, and the identification of substantial resources also from outside Cern's budget. It's very important for the implementation of the first stage of a possible future project. In addition, there is the optimization of the design of the colliders and their injector chains. Of course, the elaboration of a sustainable operational model for the colliders of the experiment, and this includes also human and financial resources, but also environmental aspects and energy efficiency. Last but not least, it is very important to consolidate the physics case for both physics case and detector concepts for both of the two colliders, so EE and HH, hadron. So the feasibility study will have to be finished by the end of 2025, as we said, in time for the next strategy upgrade. We see here, as I mentioned before, the feasibility study, one of the highest priorities, identify one of the lowest risk placement, and well, in this plot before, some regions of risk are identified already, as have been identified, and they have to be optimized with respect to that, and also the design of the accelerator. So currently, the option preferred for the moment is a model where there are 8 surface sites with 8 fourfold symmetry. And this allows for 4 interaction points that are here indicated, and allows that for FCC to choose between 2 or 4 interaction points. And in addition, there are 4 technical sites, basically midway in between the interaction points. The studies related to this implementation are one of the focal points right now of the feasibility study, and the goal is to confirm this baseline design by the FCC week in June this year. The organizational structure of the FCC feasibility study is shown here. So it has been set up. Basically, we have, so there is, the Cern Council, and below that there is a supervision layer that is composed of a steering committee that talks to the Collaboration Board and Scientific Advisory Committee. And below that, there is the execution with a coordination group and the different, let's say, working groups or working packages, so physics experiments and detectors, accelerators, and so on. Technical infrastructure, civil engineering, host state processes, organization, and study support and coordination. Okay, I'm moving now to a little bit further. So as I mentioned, there are 4 different possible accelerators. There are also 4 different communities working on developing their new machines. And it is important, however, to keep a coherent strategy, and, well, let's say, to share challenges and expertise between all these different communities, such a way that we can better explore also the synergies and efforts, okay? So ECFA, in recognition of this, ECFA has started to organize a series of workshops towards on E+ physics, towards the future machine, with the goal of bringing the entire E+- Higgs factory effort together and foster cooperation across various projects. And this will bring also collaborative research programs in future. So this study has been launched, and working groups have been created, and they have initiated their activities with several kickoff workshops and topical meetings happening these days. So there is 3 different working groups: physics working group 1 on physics potential, another one on physics analysis methods, and the detector R&D. The first workshop on E+- Higgs electroweak top factories will happen in Hamburg in October this year, and it will bring up the community together to discuss the status of the different working groups and also future plans. Also to foster interaction between theory and the experiments. Essential. So this European strategy also includes other points of attention. And there is a topic particularly on essential scientific activities for particle physics beyond beyond colliders. Okay, this is the base of the Physics Beyond Collider program at Cern and in other national labs. So the basic idea here is that the quest for dark matter and the exploration of flavor or fundamental symmetries are crucial components of the search for new physics. And this can be searched in many different ways, and there are complementary strategies. So precision measurement of flavor physics or electric dipole moments, searches for actions, dark sectors, and feebly interacting particles. And therefore, it's important to keep and maintain a diverse program that is complementary to the energy frontier. And this should be also an essential part of the European strategy, basically. And experiments in these diverse areas can offer also potentially high impact in particle physics program at laboratories in Europe, and they should be supported, as well as the participation in experiments of this kind in other regions of the world. This was the statement in the European strategy. And this is paradigm in the search in BSM physics. We can see that basically there are complementary strategies to search for BSM physics. On the one hand, we have the energy frontier, where we have the LHC, and this is a graph where you see the interaction strength versus energy strength. So on the higher top, we have LHC, future circular collider, or whatever. And in the lower intensity region, in the intensity frontier, we have experiments such as neutrino physics, flavor physics, the hidden sector, and so on. So many new ideas are emerging, and there are many different experiments proposed to cover also this other, diagram, let's say. As an example, there is here this plot on the an example of reach of different experiments. So you see here the mass of the BSM beyond the standard model particle. This is a logarithmic scale, okay? And here you see the coupling strength. The LHC is here at the high energy and high coupling strength. While there are experiments such as EDM or other non-accelerator projects that can cover this region, this very low mass domain, and also in some cases very low coupling strength. SPS experiments such as beam dumps, searches for long-lived massive particles, and so on. These ones here, they can probe the MEF to GEF domain, as you see here. So it's a complementary approach that we should follow. Okay. There are new experiments at Cern, at the LHC already to search for long-lived massive particles. We see here some of them. Millikan, that is close to the CMS interaction point, is already in construction for run 3. Phaser, search for dark photons and TeV neutrinos, 480 meters far from Atlas interaction point, or SND at the LHC, TeV, search for TeV dark neutrinos, sterile neutrinos or dark photons here. The Cern, okay. We have also the Cern proton beam dump facility that a comprehensive design study of this facility is being done within the Physics Beyond Collider program at Cern. Okay. Okay, I have to speed up a bit. Okay, there are some experiments planned, like a ship that will explore also high energy neutrinos and other physics topics that compete with other experiments such as NA62 and shadows. I will therefore not cover in detail this slide, but you will see some topics in this workshop, so joint activity expression 4 for the proton EDM, or the gamma factor in the talk by Krasny on Wednesday. Okay. We have, within the European strategy, there is also an important point that is, concerns the roadmap for accelerators R&D. And it is that, accelerators are a powerful driver for many, determine the physics reach we can get. And we should therefore invest in R&D, important R&D on this area. They are also important drivers for many accelerator-based fields outside high energy physics and also in industry. So it's important to develop technologies in high field magnets, high temperature superconductors, plasma wave field accelerator, high gradient acceleration structure, right, muon beams, energy recovery links. So the European particle physics must intensify the R&D on this area and provide an accelerator R&D roadmap to ensure that the technology will be ready basically in time to develop this next project. So the roadmap should prioritize technology, taking into account also synergies with international partners and other communities, such as photon or neutron sources. Okay. The implementation of this roadmap has been in charge of the lab directors group, being the group of the 10 major labs in Europe, and directed by Dave Newbold, who is the current chairperson. So the development of this accelerator roadmaps have been a very intensive effort during the 2021. You see here some of the milestones along the process. There were several expert panels in all the technologies that need to be developed. And there was an intensive community consultation phase that received the input from the accelerator R&D community and the particle physics community. And out of this consultation phase, there was an interim report that was presented last year at the EPS HEP conference in July. And feedback was also provided to the national communities via the ECFA delegates and also some the review of this accelerator roadmap was done by the Cern Scientific Policy Committee. And there was a closed process for prioritization, planning, and costing of this. The roadmap was finally presented in the Cern Council in December 2021, and the contents of the roadmap cover a broad and deep survey of each technology area of these 5 areas, the identification of key R&D objectives for short-term and long-term, definition of the deliverable and delivery plans for the next 5 to 10 years in a longer time scale, and outline the estimates and resources and needs, particularly for these facilities, okay? And also some overarching recommendations for future R&D program. So the implementation of the roadmap is now being discussed. And this, by the LDG, has been elaborated a first plan. The idea is sketched in this diagram here, where there are different working groups, basically within each of the 5 panels we saw before. And this will be coordinated through a coordination panel per theme. And this then report to the lab directors group and to the Cern Council. So this scheme is planned to be lightweight. Oh, okay, sorry, I'll try to speed up. And trying to cause minimal disruption with the system projects. And as I said, it is being discussed. I'll skip this and go to the the detector R&D roadmap. So in the similar way as the accelerator roadmap, we have we had been in charge to develop detectors roadmap with the objective basically to make sure that all the technology we need to have in order to implement these experiments you have seen before is ready and in time for the time when we want to have the next facility, okay? So this roadmap process has been developed during 2020 and 2021. The structure was, as you see here, there was a detector roadmap panel chaired by Phil Alport and with Scientific Secretary and Suzanne Kuhn. And there were several different task forces that were identified with their conveners. There was an intensive community consultation phase in a similar way as with the accelerator roadmap. And then there were meetings and discussion sessions, and there was also a consultation phase within the national community through the ECFA delegates. Finally, the roadmap was presented at Cern in December 2021 after being endorsed by the plenary ECFA meeting in November 2021. The content of the roadmap fast is, well, you will have to, you're not supposed to read this, but it's just to give you an idea. There are different technologies, and for each technology, several different themes that have to be developed were identified with different time scales. So basically, in order to achieve all the different machines, these were divided in beams of 5 years with objectives that have to be reached by the certain times in order to be able to fulfill these new facilities, with some also arrows indicating the implementation phase later on. So the roadmap for the implementation plan has been already started and is in discussion with Cern Council and the funding agencies. Okay, I will skip this. The synergies with other fields are also important, and this is, we are in a synergy meeting here. So I'll very fast come to my conclusion, sorry for the delay. And I think we have a very ambitious plan for the next years, but we have set up all the steps we need to achieve these goals. And we're in good progress also towards that. And the basically full European particle physics community must work together to achieve these very ambitious goals and be ready for the next large collider project and the next strategy upgrade.
Thank you very much, Patricia. We all know how difficult this is to take over a talk without short notice. Thank you very much indeed. But I believe we have no time for questions. You will find Patricia certainly during the welcome cocktail. But in order that the cover doesn't get warm, I think we should move on. And thank you, Patricia, once more. And third talk of this session is, of course, NUPEC, and I invite Marek Levitovic to give the presentation. Marek, please.
Thank you. So I have almost impossible task to make you awake before the cocktail. I know that some of you woke up at 3 or 4 or 5 in the morning today, so only reading the urgent emails make you awake still. So, but I will try, nevertheless, to present the NUPEC and the strategy for nuclear physics in Europe let's say, in 30 minutes. Okay, this will work. Let me start with the reminder what's NUPEC. In fact, this is the European Expert Board for Nuclear Physics, hosted by European Science Foundation, representing about 6,000 scientists, with the current composition of 34 representatives from 21 countries, which are on the right map, and also S3 nuclear physics infrastructures. The membership of the Joint Institute in Dubna was suspended in March 2022. We have also a pleasure to have 4 associated members, Cern since quite recently, Israeli Temple Labs Nishina Center, and many observers from the sister organizations from the neighboring fields and other continents. So we have regular meetings, of course, and the committee is a little bit older than the APEC that exists since 33 years, and we continue the activities. Indeed, it's on this side. So one of the most important activity of NUPEC is the long-range plan, which is established quite regularly. The long-range plan identifies opportunities and priorities for the nuclear science in Europe and provides the national funding agencies, S3 and European Commission, with a framework for coordinated advances in nuclear science in Europe. So the most recent long-range plan was established and published in 2017. Very recently, in fact, in February this year, we published the report on the assessment of implementation of the NUPEC long-range plan in 2017. And as you might see, we hope to launch the new long-range plan in fact this month. We have a dedicated meeting of the committee, which will start this next long-range plan, which will span over 2 years. What's the definition of the nuclear physics? So I tried to remind you that this is a very broad field, including strongly interacting matter, of course, hadronic physics or hadron physics, nuclear structure, which was described by Gerda in detail, nuclear astrophysics, fundamental symmetries, and interactions, and of course applications. I will not have time to enter into details, and my talk will be essentially dedicated to the strategic development of the infrastructures and some new detectors. So what I will develop in the future part of my talk, this is related both to the recommendations of the 2017 long-range plan and the most recent advances in different topics. As you see from this slide, I will start from the theory. This is the overarching part of our activities in all fields or subfields. And NUPEC, in order to pin down the existing workforces, performed recently a survey in nuclear theory in Europe. Well, you can see here a snapshot of the part of the results which were obtained. So we divided the nuclear physics into these subfields, like nuclear structure interactions, nuclear astrophysics, heavy ion physics, hadron physics, nuclei as laboratories, and then try to identify with the help of NUPEC members the workforce and also to get some conclusions. You might see here in percentage the division between the theory workforces in different subfields. And on the basis of this survey, we can draw the following conclusions. In order to have the field, in this case nuclear physics, healthy, theory, of course, activities are absolutely essential. And the numbers show that this is indeed the fact. You see here the numbers with the important number of researchers. So these are both permanent staff members and temporary staff members in different NUPEC countries. There is an approximate equivalent partition among the big fields, except the symmetry and nuclear astrophysics, but of course the link between astrophysics, nuclear astrophysics, and nuclear nuclear structure interactions is very close. We can observe the concentration of specific sites, labs, which occurs in some countries, like Germany, Czech Republic, Romania. And in some cases, for some countries, definitely there's a lower number of the PhD students and postdoc per permanent staff member. So these are the major conclusions which we had from this survey, which was only based on the numbers related to the workforce. The second point on the theory which I would like to make is that nuclear physics is happy to have important theory center, which is called ECT STAR in Trento, in Italy, which is very active, organizing the workshops, the collaboration meetings around 2025 in the non-COVID area or times, with the doctoral training programs, talent schools, and research activities performed by the local team. This center is, as you see from this side, well funded from the different countries. Of course, there's a strong contribution from FBK, Fondazione Bruno Kessler, and Italy through ENFN, but there are really many countries contributing to the funding, and there is a very nice link of the ECT START Center with other countries and also other continents. This is not only the Nuclear Theory Center, but also, as you might see from this graph, the programs related to other areas like astrophysics, cosmology, quantum many-body systems, and others. Yes. Let me go now to the strong interacting matter. Of course, this topic will be discussed also by Jürgen and presented in the several talks during this symposium. Just a reminder that we are talking about the quark gluon plasma and all related areas here. The main recommendation in 2017 long-range plan was that the synergy between ALICE, NICA, FAIR, and fixed target experiments at Cern should be developed. In the meantime, NUPEC expressed also in relation to the particle physics strategy, expressed its support for the Hadron and heavy ion programs at FCC. Here I would like to mention very recent development related to LS3, which was presented in the recent letter of intent to LHCC, with the following conclusions provided by the committee that this future project provides a roadmap for exciting heavy ion physics starting in 2035, and LS3 detector concept is well matched to the proposed ambitious physics program. And of course, I will not repeat the questions which are still open and will be open even after the round 3 and 4 for this physics. The LS3 detector is a novel concept based on the innovative technologies and is definitely relevant for the future high energy physics experiments at LHC, and not only, by the way. The physics of hadrons, the fundamental questions here are how is mass generated in QCD, and what are the static and dynamic properties of hadrons? How does this strong force emerge from the underlying quark-gluon structure of nucleons? Here the main recommendation was from the 2017 long-range plan that the anti-proton program at the Ferry Panda facility combined with programs with polarized protons in Dubna, and those with lepton and hadron beams at existing facilities, Mami, Boni, and Frascati, should be strongly supported. There is advance on the construction of Panda at FER. So this is the real photo of the Panda magnet. And there is, of course, a new player in this game, the decision which came in the meantime of the US to construct the electron-ion collider. NUPEC is supporting the European contribution to this electron-ion collider through the NUPEC EIC task force, and also contributed to have this expression of interest with, on the synergies between EIC and LHC experiments, which will be presented later on in this symposium. Nuclear astrophysics, this was already discussed today in many aspects. I will just remind also with two important expressions of interest to be presented in this seminar, nuclear physics at LHC and also gravitational waves for fundamental physics, that this is a completely new dimension which happened, and we started with gravitational waves and in the recent years, just after we published the long-range plan in NUPEC. So to tackle the different related problems in nuclear physics, here the long-range plan recommended the distributed approach and effort with different accelerator types and energies. What does it mean is, okay, so that means that there's a support and development of both smaller scale accelerators. Here is an example of Luna at Gran Sasso, and also large scale efforts at large scale facilities, shown here as an example of the mass measurements close to the R process path. And this is not only European, of course, but worldwide effort in order to get the data, pinning down more exactly this R process path and, of course, the different productions of elements in the universe. Nuclear structure and reactions, this topic was well covered by Gerda, so I would like to make just one remark here, that in the coming years, based on the existing facilities and also on the future facilities, which should enter into operation in the coming few years, Europe will really have the workhorse in terms of the radioactive ion beams at these major facilities, covering essentially the whole range of energies from essentially 0 up to GeV per nucleon if radioactive beams with very high intensities and which will allow to perform completely new experiments. Applications, you know, of course, that nuclear physics is an important source of applications. Let me mention some of them in the climate and the environment through the sun activity, heat in the Earth interior, ocean monitoring, wastewater treatment, mapping of groundwater resources, and many others. Of course, the energy through the electric power generation, but also waste management and nuclear data, through health, radioisotopes for therapy and diagnosis, as well as hadron therapy, for everyday life products with sterilization and modification of materials, for example, cultural heritage and forensics. This maybe is more surprising for you, but it's really extremely exciting topic for the applications, spectral technology and exploration, for example, with the Mars rover, which is using nuclear energy to move on. So in this context, from the nuclear physics perspective, there's importance of both of large and smaller scale facilities. In fact, most of the applications are related to smaller scale facilities in Europe. And I would like to announce at this occasion also a report on nuclear physics in everyday life, which should be published soon by NUPEC. One point on the nuclear energy in Europe, which is providing 25% of the electricity produced in the European Union. The nuclear reactors in 13 member states, more or less in the half of member states. All in all, in Europe, there are 128 nuclear power reactors, and there are today 3 reactors under construction in the European Union and 2 in the UK. And there are important plans for the construction of the new reactors in Bulgaria, France, Poland, UK, and probably other countries. Very recently, nuclear energy under certain conditions were recognized by the European Union being in line with the EU climate and environmental objectives. So this is a very important point also for the development of this nuclear energy in Europe. Of course, the nuclear physics is providing in this nuclear energy environment, the nuclear data is working for the waste management in order to find the right solution. And I want to flash just one example of the support for the MIRA projects, accelerator-driven system in Belgium. This is the project for which the phase 1 is funded, and the development is based on the high intensity 100 MeV proton machine for this first phase. On the top, of course, of the technological issues which should be checked and solved for this reliable acceleration of protons, there is also the program, the fundamental physics research, production of isotopes for medical applications and others. So there is important support also from the NUPEC side for this project. In the following 10 minutes, I will make a very short survey of the facilities and to update you what happened from the, let's say, essentially from the last Jenas up to today at different facilities. So this is the reminder of the priorities which were established through the long-range plan 2017. The first was related to the FIR facility, then to the ISOL facility, so isotope separation online radioactive ion beam facilities in Europe, full exploitation of existing and emerging facilities, support for ELIS, which I mentioned, and also support for the completion of Agatha in full geometry. Let me go quickly through the recent advances. So this is the first facility, which is S3 landmark and the top priority for European nuclear physics community today. So this is a very international endeavor in Darmstadt, which is under construction today. The full facility, what's called modularized start version, is shown here on the drawing on the right side. In 2019, there's an intermediate objective which was defined. The definition of this intermediate objective is the full scope of the accelerated experiments for the modularized start version and realization of the buildings, of all buildings, in fact, for the accelerated experimental area, except the building for CR and the storage rings and proton LINAC. And there is, of course, intense research of the additional financial contributions in order to complete the buildings which are shown here in the light green. Today, the status of the construction is that 60% of the concrete works for the intermediate objective are completed. All orders of technical building equipment for intermediate objective have been placed. 40% of the accelerator components for the full facility have been produced and tested. 46% of the experiments, very precise number, for the MSV are finalized. A few photos from this impressive construction site close to Darmstadt. You see here the GSI existing facility and the construction of FIR. Also, with a little bit more details, the construction of the site south with the very recent photo. And of course, this is not only concrete, but also the worldwide production and delivery of accelerator and experimental components is ongoing, and with many components already delivered to GSI. The next facility, in fact, the S3 roadmap facility, is Spiral 2 at Ganil. Very recent news on this facility is that LINAC nominal light beam intensity capabilities were demonstrated in 2021 for this facility, and the first PR2 experiments and neutron force science facility were performed successfully in 2021. So this part of the scientific program with neutrons is going on a smooth and regular way every year. The next parts of the facility are being progressively completed with the S-Cube separator, and then the construction of the Desir facility should start in the coming few years. The next roadmap, S3 roadmap nuclear physics facilities, ELI and P, with several important milestones reached in the meantime, with the operations since 2020, with the highest power of lasers in the world, which was demonstrated. So in fact, this is a complex of lasers at different powers, from 100 terawatts up to 10 petawatts, with the very rich scientific program, which I have no time to discuss. I would like just to say that this facility is operating as the user facility since last year, with the calls for proposals organized with Eli Eric, so other branches of Eli, for the ongoing period with different lasers of the power. Cern at Isolde, which was nicely shown by Gerda with different experiments, is the worldwide leading ISOL facility producing radioactive beams and using not at all negligible part of the Cern protons produced by the accelerator complex. And I would like to flash the midterm goals for this facility. You might see that the existing hall is pretty busy at low energy This is the low energy part of Isolde. So the midterm goals includes the new lab for nanomaterials, parallel radioactive ion beam operation, upgrade to receive higher energy protons at higher intensity, upgrade of transfer line. On the longer term, there is a very ambitious EPIC project, which includes the construction of the new experimental hall, storage ring, and currently the collaboration is working on science case before considering funding strategies for this part. The European nuclear physics community is also strongly involved outside of Europe. I put some examples here of the strong involvement. This is not the exhaustive list, of course. There are many others. At radioactive ion beam facility at Regen, there's a strong involvement, including advanced detectors. This is also the case for Triumph in Vancouver, which is constructing the new project Ariel. Right now, this is also the case for Itemba Labs in South Africa with the new projects, which is called SAFE. EIC, of course, I mentioned. That there's really a strong interest of the European community in this project. And last but not least is EFRIP in East Lansing in Michigan. This is the new radioactive ion beam facility in the US, which is beginning the operation. In fact, the ribbon cutting ceremony happened yesterday for this important facility. That's perfect. Two words about the most important development in terms of R&D in nuclear structure. This is the Agatha project, the ultimate gamma ray spectrometer, which you might see here in the final configuration, which is composed of 180 detectors with segmented crystals covering the 4 pi. With the very good energy and position resolution for the detection of gamma rays, important for nuclear physics. This is, of course, a large international collaboration. What happened very recently, this was, of course, one of the long-range plan 2017 priority. What happened recently is this signature of the Agatha Memorandum of Understanding for the following period, with the core investment of about 22 million euro in order to start the completion of the detector towards 4 pi. The very particular feature of this detector is that it's a moving detector. In fact, it's possible to move it in order to meet the best available beams in Europe. It moved from Legnaro in Italy to GSI, then for a long campaign at Ganil, every time increasing the number of the detectors. And then in this new MOU phase 2 will be progressively completed again in Legnaro and in the further step and other facilities. So the last point is related to what was mentioned also in the previous talks, these actions going towards integration of the community through the EU project, which are increasing the support for users and facilities. Very recently, we had the pleasure to work with the particle physics colleagues in a joint project. So this is particle physics, nuclear physics, joint projects, which is called Eurolabs. I think this happened for the first time that these two communities applied and successfully applied for the funding from the European Union. The coordination is done by Naveen Alahari, who is here, and the coordinating institution is CNFN, with 39 research infrastructures. Some of them I put in this list. There is also an ongoing project in hadron physics called Strong 2020, which will last still for several years with the coordinated by Barbara Erasmus for INTP3, and INTP3 is the coordinating institution. And this important project is really integrating, I think, all European facilities importantly for hadron physics. But moreover, there are also new projects from the emerging communities. I think it's worth to mention that the field, not only nuclear physics, but also other adjacent area, it's very broad. So they recently, still with Horizon 2020 projects, there were 3 of them successfully implemented, still ongoing. The PRISMA, production of high purity isotopes of mass separation for medical applications, CHETEC, chemical elements as traces of the evolution of the cosmos, infrastructures for nuclear astrophysics, and RADNEX, radiation facility network for the exploration effects of industry and research. As you might see from the coordinating institutions, again, we have here the nice synergies between different fields of science and different institutions. The problem might be how to continue these successful projects. There is no place today in Horizon Europe for this kind of projects any longer. So this was discussed with the European Commission, but still it's not the case. They cannot really continue even if they are successful in Horizon 2020. So I'm arriving to the conclusion. So I tried to present the NUPEC strategy for nuclear physics in this intermediate period between the 2017 long-range plan and the new long-range plan, which will start essentially now. The strategy pillars are the science, the interplay between theory and experiment, nicely shown also by Gerda, with the applications, with the huge societal impact, facilities in Europe, first PR2, ELINP, is all the space, and others, and also in other continents with this involvement of the European groups, like RIBF, Triumph, Emba Labs, EIC, FRIP, and others. This is not exhaustive list. I showed 2 examples of the developments of the detectors with Alice and Agatha. Data and open sciences, of course, open science is not forgotten, of course, with ESCAPE, for example, and other initiatives, and synergies with neighboring fields. This is why we are here for Jenas. Strategy development, after this definition of this ambitious strategy for European nuclear physics through the 2017 NUPEC long-range plan, we performed in the committee important efforts in order to transform this long-range plan into reality. For example, with the task force meetings in many European countries. We are starting the next NUPEC long-range plan this month, and NUPEC is contributing to the global international approach to nuclear science in collaboration with Cern, IUPAP, EPS, Air Force, ECFA, APEC, and our sister organizations at other continents. Thank you very much for your attention, but I would like to finish with warm thanks to all colleagues for their contributions, and warm thanks to Andreas and Carl for close and fruitful collaboration. I hope that Carl will recover soon from COVID and will continue the collaboration again. Thank you very much for your attention.
Okay, thank you, Mark. Thank you very much for this presentation. I fear we have overrun, and would like, therefore, to thank all 3 speakers again of this session. Okay, I close the session, and it's cocktail time, right, Maria?